HTTP on machine learning and deep learning techniques for AI problems using Python. Day 2. Today we'll have talk about exploring CNN for real-time practices. Before hand over the session to Ramalinga Swami Garu, I would like to introduce him. So, Dr. Ramalinga Swami Garu is working as assistant professor in NIT Warangal. He did his MTech at IIT Gwalior and PhD from National Institute of Technology, NIT Goa, and his PhD titled Design and Development of Efficient Soft Computing Algorithms for Identification of Type 2 Diabetes mellitus, and he holds 3 years of teaching experience and 2 years of industry experience. Presently, he is working as an assistant professor in NIT Warangal. Previously, he worked in IIIT Naya Raipur, Mahindra Eco Central College of Engineering, Hyderabad, and PVR, and as ASC in Tata Consultancy Services also. And Dr. Ramalinga Swami Garu act as co-principal investigator for the project titled Smart Agriculture for Tribes Using Artificial Intelligence and Big Data, funded by Ministry of Electronics and IT. And he had over 20 journal publications and 12 conference publications also. He holds book publications also on soft computing techniques for type 2 diabetes data classification at Taiwan and Francis. And he also had book chapters, another 2 book chapters. And his areas of interest are soft computing, machine learning, data mining, wireless sensor networks, deep learning, artificial neural networks, optimization, and big data. Now, I would like to invite Dr. Ramalinga Swami Garu to take over the session. Sir, you can continue, sir.
Yes. Okay, thank you very much. So is my screen visible? I mean, are you able to see my screen, my presentation?
Sir, visible, sir.
Yeah, okay, thank you. Good morning, all. Today's topic for the discussion is the convolutional neural networks. So, what is the importance of the convolutional neural networks? How they are different from the conventional neural networks? So, what is the significance of these CNNs? What are the applications where we can use these CNNs in real time? The time permits, I will also discuss about the different CNN architectures. So what are the traditional neural networks? So by this time you're already familiar with what is the traditional neural network. Like if you take a multi-layer perceptron or multi-layer feed for a neural network. So these traditional neural networks have certain limitations. Okay, so we cannot apply these traditional neural networks on image data. So why? So if you see that. If image is represented as a pixels, okay, if you know that image is represented as the pixels of it, and if you take in a black and white image, so in that case there is no RGB. If it is a colored image, it has a RGB case. It has a 3 layers. We can it's a 3D image. Okay, in case of RGB and so when you take any particular image, so each image is represented as pixels. Suppose if I take so why my okay. So if you assume that each and every pixel as a one of the feature, and you know that the traditional neural networks, you have input layer, hidden layers, there are multiple hidden layers and output layers. So obviously you know that the number of neurons at the input layer, if you take any neural network, the traditional Mldlt or MLFFL or RBFN or probability neural network, in any neural network, traditional neural network, the number of neurons you have to keep is equal to the number of features. But in case of image, the number of neurons you have to keep is equivalent to the number of pixels in your image. Because each and every pixel we can treat it as one of the features for classifying or your image. Suppose if image of high dimensions, if you take image of suppose here if I say the 224 by 224 pixel image with the three color chart, if it is RGB or colored image, then there are around 15,000 pixels will be there. So even input layer of size such a huge, and as a result, there are certain difficulties in the training such a huge complicated networks, and sometimes it leads to the overfitting. So I know that what you know the overfitting, because in case of overfitting, we will see how this overfitting problem can be solved soon. So in case of overfitting, what will happen? Your network will try to learn the whole training data. So in that case, what will happen? The regression capability of your neural network will degrades. Means it works well for the training data, but it may not work for the testing data. It works because why? Because it's already learned the inherent features, the inherent capabilities inside your training data, known data. So as a result, once it learns the inherent features, the dependency among the features, once it learns, so it won't perform good for the unseen data. So that is the reason the overfitting will occur. Overfitting will occur most of the time because of if you train your network too much for too many epochs. If you train your network for multiple epochs, so then this overfitting can occur. So that is one problem. The one problem, the traditional MLP or MLFFN is overfitting problem. So that is so as a why here I am highlighting why the traditional neural networks we can use the traditional neural network, but it has still some drawbacks with respect to the image data. So there the concept of convolutional neural networks is came. So then another common problem in MLP is what will happen. So these MLPs, the multi-layer perceptron, the traditional neural network, they fail to identify the shifted version. Suppose you have taken one image to classify whether which you have used for the classification purpose. So there is a cat image is there. In one image, it is able to say that the topmost right corner, and in another image, the same cat is there, but in the bottom right. There are two images, but in the two images, the cat is present, but the location is different. The spatial arrangement is different. So what case these spatial arrangements cannot be handled by this traditional neural networks. So that is one more reason. So why these traditional neural networks fail to effectively classify the image data. If you look at another problem of this image processing to classify images and in image processing area is the spatial information is lost when the image is flattened into the MLP. So give me some time. Why my pointer is not working? My stylus is not working. Give me some. Okay. So what happened with this PPT? Are you able to see my whiteboard?
Yes, sir.
Yes, sir. Okay, so that I want to draw something on this. So what happened? So what is the problem over in traditional MLPs? So what is the point? If you look at here, the image is flattened into the MLP. So what happened when you flatten the image into this flattened MLP? So it lose some kind of spatial information. What is my flattening over here is, suppose there is an image. So here taken 3 by 3 image. So what I will do, that each and every pixel has a one feature. So there are total 9 features. What I will do, so I will flatten this image, one image pixel 2, 3, and so on. Up to, and this is called flattening, and this is fed to the traditional neural network. If you feed this traditional network, what will happen? So this will cause a loss of spatial information. For the timing, you remember that what is, just remember that if when you flatten, it will cause the losing of the spatial information. I will discuss more in detail in coming slides. What is maybe spatial information? How do we overcome this flattening problem? So as we know that if you want to supply the features to the MLP, multi-layer perceptron or multi-layer feed format, you have to flatten your network. You have to flatten this. So when you flatten this, the problem is spatial information is lost. Then how do we overcome? So, but in case of MLP, multi-layer perceptron, there you have no option. You have to flatten your image and you have to provide to your MLP. But when you are providing like that, so what is the problem? You are losing the spatial information. So how do you overcome? How do we tackle this problem? We will see soon. So So there are, what are the problems I discussed? The one is the, when you are flattening your image, so you are losing the spatial information. And another problem is when your image is translation invariant, means, so when you are the translation invariant, suppose when you are changing the direction of your image, your ML, I mean, suppose you have one cat, you have transformed this into some, so if you rotate that particular image, your ML, multi-layer person may fail to identify. So it is not a translation invariant. So one other problem is the overfitting problem. Because of these too many features, when you are flattening, what will happen? The size of input layer increases, and as a result, the training time will be more, and it leads to the what will overfitting problem sometimes. So there are three issues we mainly highlighted. So to overcome, so from these three issues, we can say that the traditional neural networks are not effectively used for the image processing or image classification or object detection and all. So that is the reason we went for the deep learning architectures, and especially the convolutional neural networks. So especially these convolutional neural networks are used for the image processing and to classifying the images and all. So these CNNs are well suited for image classification problem when compared to the traditional neural network. Just I highlighted what are the three drawbacks of the traditional neural networks, why they fail for the image classification problem. Hence, so in case of deep, if you look at the deep learning architectures, so we will, what is your deep learning? Just increase your depth of your traditional neural networks. So when you are increase, then usually when you are talking about the traditional neural networks, usually we will have, so input layer and output layer is by default. So if you take any neural network, you have one input layer and only one output layer. The only thing is that how many number of hidden layers. It varies from the layer architecture to architecture. So what is called deep neural networks? When you increase this depth of these hidden layers. So far you might have seen for 10 or 20 hidden layers, but in case of deep learning networks, we will use hundreds of these hidden layers. Okay. So when you, this is mean by depth, increasing the depth of your traditional neural network is called deep neural networks. Okay. So usually that is meant by deep neural network. So we can in layman terms we can say that when compared to the traditional neural network, deep neural networks will have more number of layers. But there are so many such architectures exist for specific to the problem. So when you take the time series data, we will use recurrent neural networks. When you take image data, we will use convolutional neural networks. Okay, so today topic we are confined for only convolutional neural networks. So in the year 2012, of course, the convolutional neural networks have been since long time but it has gained attention in the year 2012. This convolutional neural networks are not new to this neural network community. They were there since long time, but they have gained attention in the year 2012 in a so one of the neural network competition or image processing competition is called ILS-VRC. It's the annual competition in the area of computer vision. So they will give some kind of problem statements. So different kind of participants have to come up with a different kind of model to provide the solution to those problems with better accuracy. Not only provide the solution, you have to provide the solution with the better accuracy, provide the better accuracy. That is the aim of this it's annual conference, annual competition. So in that competition. So this first and one such a deep neural network algorithm is exploded to solving a particular problem. So that network they named as a AlexNet. So this is the first time we gained the attention about people are turned about. They started talking about deep learning algorithms. So it happened in the year 2012. So with the AlexNet. Okay. So we will talk about this. Then started the Alex node. Now recently, the recent convolutional neural architecture is a ResNext res residual network. It's some variant of the residual network. It was came in the 2019 also. So there are every year they are giving some kind of improvement in this ILS VRC competition. They are giving every time they are coming with the different CNN architecture to solve the problems with a better accuracy. So AlexNet is one such CNN architecture. So we will talk about the architectures later once we have time with us. Okay, once we discuss what is the convolutional error, what is the convolutional neural network, what are the problems are there in CNNs and all. The convolution will have a methodology similar to that of traditional supervised learning method. They receive input images, as I told you that the CNN neural networks are, are specifically for the image problems. Okay, to deal with the images. Okay, input image detect the features of them and the dragging grader on it. So basically this convolutional neural network, the advantage of this convolutional neural network is they will automatically identify the features. Okay, they will automatically detect the best features in your image. That is one of the beauty of this convolutional neural. How it is identifying, we will see soon once we are discussing in detail about CNN. So, however, the features are learned automatically. Just I told that the features are learned automatically. The CNN themselves carry out the tedious task of extracting and describing features. So there is no manual intervention is required. So earlier, what we used to do, the user has to handcraft the features. The user has to handcraft the features. But this task is a tedious because you need to have a good domain knowledge. Unless until you don't have good domain knowledge, you cannot carry this handcraft features. Okay. So, but the problem is completely bypassed in case of CNN because just give the image, it automatically extracting the features, the best features for your problem from that image, the best feature, the high level features or the problem specific features of the particular depending on the architecture. So it automatically so that's the beauty of the CNNs and it reduces so much of tedious work from the user point of view. So apart from that, and when compared to with respect to traditional neural networks, still again we have a training phase and testing phase, and we will have we are trying to minimize the error function or loss function, and all those things are similar to the traditional neural networks. So, what is the CNN? Convolutional neural network refers to subcategory of neural networks, and they have all the characteristics of the neural network. As I said just now, so they have all the characteristics. So we have a similar to the traditional. You have a training and testing, and you have a gradient. I mean, you have to find the loss function. You have to identify the error at the output layer, and you have to back propagate to the input layer. All these are some of the characteristics which are similar to the convolutional neural networks, similar to the traditional neural networks. So the same thing applies for the CNNs also. However, CNN is specifically designed to process input image. This is very important. The CNN is one of the deep learning architecture which are specifically designed for to process the images. and their architecture is more specific. It is composed of two main blocks. Okay, so now, two main blocks. Sometimes we can say that the CNN consists of four layers and all those things. So if you say that the first block makes the particularly of this type of a neural network since it functions as a feature extractor. So if I visualize the CNN as a two blocks, the first block and second block. The first block is a we can say that it's a feature extractor. So it functions as a feature extractor. And once you extract the feature, what is the remaining task? The second block. So what the second box? The second block, the second box is similar to the your. So what is the difference between the traditional suppose if I say the traditional neural network, if I'm talking about in case of traditional neural network, you have a features, and so this feature is nothing but input layer, and you have a hidden layer and the output layer. So there are multiple hidden layers. I'm not also there are interconnection between this. So 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 this port is same. This port is same. So in case of CNN also, this is called with respect to our PPT. This is called second block. So what is the first block is talking? So this first block is a block. So we will talk about inside what is there in the first block. It will provide the features. The output of this first block is features. So once you have features, this is your input layer, and this is rest all is same. So this is called feature extractor. As I told that it automatically extract features. So this part is done at the first block. So we will see what are all there in the first block, and the second block you are already saying that it's similar to the traditional neural network. Sorry. So am I clear? So that how the difference between CNN. So this all together is a CNN. So this second block is a similar to the traditional neural network. This first block is talks about the feature extraction. So what are all the feature extraction? How the CNNs is extract the features automatically? We will see soon in the coming slides. I hope you are clear. Uh, so this the same thing I kept here. The first blocks particularly of this type is a neural network since this functions as a feature extractor. The feature extractor. And to do this, it performs template matching by applying the convolution filtering operations. The first layer filters the image with the several convolution kernels written feature match with then normalized. Okay. So what actually it does inside this first block, it will talk. It will do some kind of the convolution operation. So if you look at in image processing area, so what is the convolution operation? So if you take the some inputs from the convolution operation in the image processing and map those inputs to the convolution CNN networks. So in case of what happened in case of convolution means the convolution operation means you can stride over it's kind of a what you call the stride over operation. So what will happen in case of that is mean by as that is the reason it is named as a convolution neural network because it will perform some kind of convolution operation. What do you mean by this convolution operation means? So if you take so what do you mean by this convolution operation? Suppose there is an image. So there is an image of 3 by 3 And there is a one filter. I will talk about what is this filter and all. Okay, so there is a filter. So 2 by 2 filter or for the simplicity purpose. Uh, so what is mean by convolution? The striding over filter over an image. Suppose it has a value something like this 1, 2, 3, 4, 5, 6, 7, 8. It has some fixed values. It has a 0, 1, 1, 0. It is a filter. Some have some weights called weights also. So I will talk about these terms later. Suppose what is meant by convolution operation means you have to convolve this filter. The convolve is rotate. The convolve filter over image. What does it mean by? So you have to convolve you have to put your this is here is 0, 1, 1, 0. So what is the convolution? You have to do the dot product of this 0 into 1. This is 0, 1 into 2, 2, 1 into 4, 4, and 0 into 5, 0. So total is 0 plus 2 plus 4 plus 0. So once you are getting one output, this is called convolved output. This is called convolved. So this is called a convolution. The striding, the filter, about strider, this convolve this filter over entire image, not a single. This is your filter on entire image. So when you perform an entire image, you will have another map. You can call it a map or activation map or something, convolved map or convolved image. You can call it. You can name anything. So this is called convolution operation. This is the basic funda behind, the basic crux behind the what you call in convolution. What happens? So what happens when you are convolving over your filter over image? What is happening? So yes, I'm taking one filter and I'm applying over the image and convolving over image. What is happening? So when you are convolving over the image, what is happening is, so it is highlighting some features. It is highlighting certain features and it is degrading certain features. So what are the features are highlighting? So we are strengthening some of the features because of this ones. You are degrading some feature. You are reducing significance of certain features in overall image by putting 0. It may not be 0, 1, 1, 0, but just I am telling, just easy understanding I have taken. So what is happening when you are saying putting 0 and 0? What is happening? The features which are correspond to these two locations are have no, they don't have much significance the overall image classification. The features which are corresponds to these to have major impact. You are increasing their significance in overall classification or to improve their what is you are increasing the strength of those features. It's nothing but you are increasing. What is happening? You are convolving this filter over image. You are increasing strength of certain features and you are degrading strength of certain features. We will see. So there are certain visualization slides are kept inside this presentation. So at that time we will discuss more. Just as so, this is a convolution operation. So this is happening at the first block. So apart from that, this convolution operation, it also performs certain operations. So we will also discuss those operations soon. So this I say just for visualization purpose I kept. This is, you can call it as the first block, and this is the second block. This is compared. This is second block, and this is the first block similar to the. So this is our first block, and this is the second block. This particular time is. So this second block similar to the traditional neural networks. The first block contains so certain operations. So the one such operation is convolution operation or convolution. There are certain other operations also there. I will discuss at that time. So like pooling layer and radio activation function and output layer. The second function and this particular thing you already know what is the softmax and logistic regression. So when you are at suppose there is an output layer, okay. This is the output layer. So this I am not talking about. So if I talk about here, this particular, this is the output layer. The last layer is the output layer, right? So if I say the output layer is like this, so there are certain output layer. Okay, this is the output. There are three new. Some there can be any neurons, one, two, up to n neurons. Suppose if there are only, if you are doing the only binary classification. So you have to use only two neurons. So in that case, logistic function is sufficient. So what? 1 by 1 plus e to the power of minus x. Suppose if you are using what you call the multi-class, if you are solving the multi-class, there are more than two classes are there, then you have to use softmax. It's nothing e to the power of minus x by normalized value. So e to the power of x by so, there are 10 clauses. So there are 10 clauses. Then what you are doing normalization. So here normalized values. So what is happening? So the normalized value of class 1 and class 2, like C1, the normalized value of class 1 and class 2 plus up to class 10 will be equal to the 1. So that is the main motor. So what this is called softmax. What is the softmax function? This normalized value, you have to divide this normalized value with respect to the class 1. This is like C1 by C1 plus C2 plus C10. This is the probability of class C1 belongs to sample belongs to class C1, and C2 by C1 plus C2 plus like this. So when you are summing all these values, C1 by C1 plus C2 plus and all plus C2 by, so this will be 1. It's called normalized. Okay, this is called softmax function. This you are already familiar. So when you have a multi-class problem, so this is softmax function. So when you are using logic 2 points, logistic binary classification, this is sufficient. So, okay. That is as far as the output layer is concerned, and also it's similar to the what you call traditional method. We can also use different loss functions like mean squared error or class entropy like that. Okay. This is second block. So this I am talking about the second block, which consists of output layer. Here I have taken a softmax function usually because we are dealing with, most of the time we are dealing with the multi-class problems. So when the multi-class means when the number of classes more than 2, then you are doing the softmax function as a activation function at the output layer neurons. Okay, that's very important. Softmax. Okay. And another important thing here is this Rayleigh activation function. I will come about this slide. So as I said that apart from this, you know what is the convolution operation? What is the purpose of convolution operation in the first block? So once you do the convolution, so we will also discuss about the max pooling and Rayleigh activation functions. So now, so as I said that in the first block, if I talk about the first block, I am talking about the first block. There are convolution operation is performed. There are, so that layer, wherever the convolution operation is performed, that is called a convolution layer. And similar to the convolution layer, there are pooling layer, and sometimes you can use the Rayleigh activation function. What is the significance of the Rayleigh activation function, and what is meant by fully connected layer? This fully connected layer is called second block. Okay, here I kept together the different layer. So this three will talk about the first block, and this fully connected talks about the second block. If I talk with respect to the blocks. So what is a convolutional layer? So as I said that the convolutional layer is nothing but when you are convolving a particular filter over the image. So that is called, the output is called feature map. That is, output is called feature map or convolved output, which tells us where the features are in the images. The higher the value, the more the corresponding value in the image resembles the features. How we are strengthening the image? Because it's this filter will help us to strengthening certain features and to degrade the significance of certain features in the overall image. As I said that, so this is my image and this is my filter. Okay, so this also filter is also called the convolution kernel, or some terminology we can call the convolution kernel, and sometimes it's called the weight also. With respect to traditional neural, these are the weights actually, but in case of convolutional terminology, it's called convolutional kernel or filter, whatever you call it. So what is the convolved operation? Just write over this particular convolved kernel over this filter over the image and do the dot product. Do the dot product so that you will get only one output in the feature map. This is called a feature map, right? This is feature map. So unlike the traditional method, features are not predefined here because the features are not predefined because the features are extracted automatically from the first block. So in the first block, one such operation is a convolution operation. Okay? So they are initialized and updated background using gradients. What they are saying that what they are saying that this is called a weight matrix. This convert filter. This what are the values? These are called weights. So these weights are adjusted during the back propagation. That you know how the weights are getting adjusted using the back propagation algorithm in the traditional neural net. So what is one another layer? So I will talk about this convolution layer, pooling layer with respect to some particular example. I kept those slides. So let me first briefly introduce what is the pooling layer and convolution. So when convolution layer, so filter is striding over across the image. You will get one output that is called a feature map. Okay, what is the size of this feature map and what is the size of this filter? What is the relation between this filter and input image and the output image? The feature map we will see soon. Okay, there. So what is the pooling layer? So what is the pooling layer? What is the pooling layer? This type of layer is often placed between two layers of the convolution. So what is it? So we cannot keep multiple convolutional layers. So what people sometimes do that in between these convolution layers, sometimes we can keep pooling layers. So what is the advantage of keeping these pooling layers between the convolution layer is it receives the several feature maps and applies the pooling operation to each of them. So the input for this pooling layer is from the convolution layer. So from convention, the input comes and this and you will apply the pooling operation. So the pooling operation is concerned what it does, it reduces the size of your input image. So what is the from the convolution you will get feature map, right? As I said, it is a feature map. To reduce the size of this feature map, you will use the pooling layer. How it will reduce the size of the pooling map image while preserving the importance characteristics. Right? And also, of course, when you are what is the problem with when you are reducing the size? Sometimes there is a chance that you may lose certain features. Obviously, when you want to reduce certain features, so what you have to ignore those features. How do we decide which features you have to ignore and which features you have to choose? So that is the task of the pooling layer. So usually we will use the max pooling. So what is mean by max pooling? In case of max pooling, we will pick up the pixel which is having highest value. That is mean by max value. Preserving, so that is mean by, so when you are doing so, when you are doing the so means when you are extracting maximum value, so what will happen? So you can some extent preserve the importance characteristics of the your image. So we should not lose that. That's very, very important. So this is called um, pooling operation. Then how do we perform this? What we do to do this pooling operation? We cut the image into regular cells exactly. Then we keep the maximum value within the each cell. In practice, small. So usually we will use 2 by 2 cells, or sometimes we can use 3 by 3 cells with overlapping. So with overlapping, this is adjacent cell with do not overlap. So what is meant by it? Okay, suppose if it is there, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And this is 1, 2, 3. This is my image. So there are some values. What I will divide this into rectangular cells of 2 by 2. If I am saying 2 by 2 means this is one such box and this is one such. So from this you will extract max. This is max 1. From here you will extract max 2. From these 4 cells you will extract one max. This is max 3. This is extract max 4. So from 16 by 4 by 4, from 4 by 2, the output is 2 by 2. When you are applying maximum pooling, what is happening? The 4 by 4 image is converted to 2 by 2 image. So that is the reason we will use reducing the size of the image. We have to use the pooling operation. Sometimes it is necessary. So we will see why it is. What is the significance of this pooling layer? So that is mean by it need not to be 2 by 2 adjacent cells. This is 2 by 2 adjacent cells. Do not overlap. Sometimes we can use, if you want to use 3 by 3 cells, but we can use with overlapping. Like this is 1, 2, 3. This is in case of 3 by 3, it will be like this. In case of 3 bits, how it look like? One, two, same problem. 1, 2, 3, 4. 1, 2, 3, 4. So if I want to apply, so this is one such box. 1, 2, 3, 3. This is a 3 by 3 cell, right? So another 3 by cell is 1, 2, 3. So this is another. This is called overlapping. You can use 3 by 3 cells also, but with the overlapping key can be allowed there. If you want to use 2 by 2, overlapping is not allowed. You can use 2 by 2 adjacent cells. So the beauty of this pooling way, it will reduce the size of your input. And at the same time, it also preserve the important characteristics of your image. So if you so far you know that by this time you know what is the activation functions and all. So I will come to what is why we are using the ReLU activation function. What is the ReLU means? The rectified linear unit. So you know that what are the activation functions? You know sigmoid activation function, uh, and another one is threshold logic, and the third one we have to sigmoid and tan hyperbolic. So these are three different activation functions we will study in traditional neural networks. So what is the problem of using these traditional neural networks activation function? So if you use the same activation functions in the deep neural networks, so as I told you that in case of deep neural network, when you are using too many layers with these activation functions, it causes the problem of vanishing gradient problem. That is called. So there is a problem called vanishing gradient problem. I will discuss particularly vanishing gradient problem at some other time. I mean, in coming slides. This is not right time. Just I'm telling why in the deep neural networks these traditional neural network activation functions are not used, because if you use those neural activation function, it causes this problem, vanishing gradient problem. What is the vanishing gradient problem? So I will discuss at that point. So to overcome this problem, we will use the ReLU activation function. So what is the ReLU activation function? It refers to the rectified linear units, and the function is like this: max of either 0 or the positive value. Where is the input? So it means that if you take a graph for this, so what is doing? So it's not allowing the negative values. If you see the ReLU correction layer replace all the negative values received as inputs by zeros. So whenever its value is negative, it puts at 0. If it is a positive value, that value is a max of 0 comes to negative value. So there is a max of 0 comma minus. What is the max? 0. So it means if there is a negative value to replace by 0, if it is a positive value 0 comma 0 0.5, it is 0 0.5. So that is mean that that's the essence. The slope is there. So this is the special activation function rectified linear used in CNN or deep neural network. The reason is vanishing gradient problem. I will discuss it. Right. Okay. Now, so far we have seen convolution layer and pooling layer and ReLU. What is the purpose of ReLU? Okay. So these three functions constitute the first block as per our presentation and as per my terminology. So what is a fully connected layer? So means once you perform the convolution and pooling layer, and in the by keeping this ReLU activation, sometimes you can keep this ReLU activation. So these we will call first block. What is the output of the first block? The output of the first block is features. So once you have features with you, so what you can do, you can connect traditional neural network. You can construct a traditional neural network. This is called fully connected layer. This is called FC, fully connected. This traditional neural network is called fully connected layer. So what is my fully connected? Traditional multi-layer perceptron or multi-layer. What do you call multi-layer for field forward network? But the only thing is the activation function is different. The activation function here is the ReLU activation function, not the sigmoid. But what is the activation function at the output layer? What is the activation function output layer? So here in this tradition there is an output layer here. Okay, the input layer is this one. This is input layer is from this feature. and in between there are hidden layers and output layer is there. What is the out or activation function? If it is a binary classes, it is a logistic, otherwise softmax activation. This is all about the fully connected layer. It allows the last layer of the neural network. Last layer of the neural network. This type of layer receives the input vector and produce a new vector output. To do it, this already discussed. What are the it's similar to a traditional neural network, and output layer will have both either logistic or softmax activation functions. So and yes, I told that the weights like this. It will be like this. Okay, if I say this is a my image, and this image will go to the convolutional layer, and there are some pooling layer, and there are ReLU layer. And so what is the output of this? If I put together, so what is the output from this? The output from these are features. So what are these features? So these features as an input to the fully connected layer. This is called fully FC, fully connected. What is fully connected? It has an input. So this is an input layer. This is hidden layer, similar to your output layer. So these are connections. That's all. This is similar to a traditional neural networks. This all together is called the CNN, convolutional neural network. And what is the activation function at this layer? The activation function at this layer, either softmax or logistic. And what is the activation function here is ReLU. Okay, that's the difference. Here it not be sigmoid and all, but the reason for this ReLU activation function is to overcome the what is the problem? What is the problem? What is the problem with this traditional activation function? It is called vanishing gradient problem. This is if I summarize that. So yes, as I told you, there are certain parameters. Okay, so if you look at this convolution has certain parameter, pooling layer has certain parameters, this ReLU has certain. So every layer will have certain hyperparameters. So these hyperparameter has to, how do you fine tune these hyperparameters? These hyperparameters you have to fine tune during your training process. Okay, so training process is back propagation training. So this is the forward pass and this is the backward pass. During that time you have to train all these hyperparameters. So what are the hyperparameters? We have to fine tune from user side. Okay, a convolution layer differs from the another way that that layer is a stacked but a parameter, but also parameters. It's nothing but it has a certain parameters. So what are the parameters are there? So if you look at the parameters of the four hyperparameters, those parameters are the K. So how many number of filter? How many filters? You need sometimes what is happening? You cannot apply only single filter. So you have to apply multiple filters. How many filters you are applying? So what is the size of what the size of F filter? What is the size of each and every filter? So this is if I take this is 2 by 2. F is equal to 2 means I am using 2 by 2 filters. This is 2 by 2 filters. 1, 2, 2 by 2 filters. F is equal to mean. How many such filters? How many such 2 by 2 filters? That is talk about the K. So and the step size. What is the step size? How many pixels we have to stride over? How many pixels we have to stride over? Suppose this is my input image and this is my what you call it's a filter. So how many pixels? So when you are placing like this, so how many pixels you have to skip? So how you have to stride over? You have to stride over from left to right and top to bottom. So what is it? So this is left to right. You have to stride over left to right and top to bottom. So I will animate this striding over operation in coming slides. Okay. This is the image striding. How many pixels you have to stride? You have to skip to perform the next convolution operation. The zero padding. So it is what is meant by padding and all these things. So padding means sometimes it is necessary to add some extra features. extra features, some null features you can say that. Add a block of control p pixel thickness to the input image of the layer. Sometimes what will happen, we will add some extra features to the input image like zeros. It has no significance. Okay? We want zero padding. This is called zero padding. We will add, why we will add this? We will talk soon. Okay. So the reason for adding this zero is to retain your input image. Okay. To retain your input image size, because when you performing the convolution operation, what will happen? The size of the image will decrease, and after performing the pooling operation, it further degrades. The size of your input will get decreased. But I don't want that. I mean, I want to retain the size of my image even after convolution pooling operation. Then you have to use the zero padding. So you have to add some extra features, which are null features to your input image, so that you can retain your input. So this is without losing. When you are adding to nothing will happen without losing any information. So this is sorry. This is called convolution layer. Something. So for each input of size, so there is a input. So if I visualize in a three-dimensional, if it is RGB, so it has a width, height, and a depth. So in case of 3D, the pooling rate is a matrix of dimensions. So when you apply the convolution operation, so you will get one feature map. So what is the size? What is its size? If I say it is WC and HC and DC, if I call width of the feature map and after convolution, W is the width of your actual image, where F is the what is the size of your just I spoke. What is the F is size of your filter plus 2P. What is the P? The P is your pooling padding, zero padding. How many paddings you are doing? Okay, how many layers of padding you are doing? One layer, two layer, or like that. Okay? And plus by S. The S is nothing but striding over operation. So when you are striding over like this, when you are striding. So how many pixels you are skipping when you perform the next convolution? Okay? So that is meant by striding. Okay. S. The formula for this is if you want to get the width of the feature map after the convolution operation, W minus F plus 2P by S plus. The same thing applies for the height also, and this is very very important. The number of the depth of what is the depth? The depth of feature map is equal to the K. What is the K? Number of filters. Number of filters. That's very very important. And there are something. Okay, if you take these formulas, suppose if you substitute P is equal to the padding. If you use F minus 1 by 2, if you are that many level of padding and S is equal to 1, if you one step striding, then you will have same width and height of the received image. Then there is no decrease in your height and width of your actual image. So there are some. If you take this one, if you substitute this, you will get this. Similar to this is about the convolution layer. So what about the pooling layer? Similar to the pooling layer, convolution, there are two hyperparameters for your convolution pooling layer. Also, one is the WP. What is the width of your our image? Your image after performing the pooling operation is W minus F by 2 plus 1, and here it is. So F is the filter size by this one. Where D, this is very very. This is very, what is the D over here? So where D is the depth of your actual image. Okay, where the D is the depth of your actual image. Where W is the depth of your actual image, H is D is. So what is happening here? The depth of the input image is same as the depth of the image after the pooling up. That is the conclusion, right? Deep image. So this is input image depth, and this is the output image depth. Both are same. dp is equal to d means the depth of the output image from the pooling operation is same as the input image. This some if you substitute some formulas, some values for FNL, you will get something. So this is a traditional. Suppose what is the typical values for this striding over operation, what is the pool, what is the how many number of layers, what is the zero padding you have to use, what is the size of the filter. So we usually will use f is equal to 3, s is equal to 1, p is equal to 1. Sometimes we can also use, there's some of the typical values for practice. I mean, some theoretical observations that these are the optimal values for these three hyperparameters. That's what we say. Okay. Now I will explain some more some in detail about each and every layer. We have seen convolution, pooling layer, and ReLU, some ReLU activation function and all. So if you look at, suppose this is a 4, this is the image 4. Okay, this is I have written image 4, right? This is image 4, alphabet 4, right? I have written 4 like this. So what is happening when you written 4 like this? So some wherever you have a 4 is highlighted, 4 is there. If you look at the highlighted portion, it look like 4. But in the remaining portion, the pixel values are very less, and this particular region, the pixel values are very high, so that we can visually say that it is a number 4. How it's an image look like? So when you draw an image like this, so this is the pixel representation. You have to convert. So what you are doing? You are flattening it. This is called flattening. These things I already discussed, but just I want to go in detail about these things. So when you are flattening, this is the actual image. When you flatten it, so what is the problem? So you are losing spatial information as a spatial information. Okay, it's impossible even for a human to identify this is. By looking at this, we can say that it is a 4. But by looking at this, we cannot say it is a 4. So it's impossible even for a human to identify this representation of number 4. We have lost the spatial arrangement of pixels completely. So it means this is not a good idea. Yes. Then other idea. So what we did here, then how to preserve the spatial representation? The question arises, then how do we preserve the spatial representation? So what we can do in case of preserving the spatial representation, if you look at here, so what I did in case of now question is how to preserve the spatial representation. To preserve the spatial, this is my actual image, and this is my filter. If you see, after applying this filter, suppose there is a filter called, this is filter are nothing but weights. We can also call weights in film. So these weights after, so what is the convolution operation? This thing is stride over this, I mean, over this like this. If you see visually, I think it's here, here. So when you are multiplying dot product, so 86 into 0.3, okay, something like this. 4 into 0.3 means 1.2, so 87.2. So like that you will get all those values. Here visually you are seeing that, visually you are still able to identify that this is a 4. Still you are able to see it is a 4. If you see itself, still it is a 4. So even after applying this filter, but what is the problem here? 1, 2, 3, 4. It has a 4 columns. It has a 1, 2, 3 columns. And also one thing you can notice that, so there is this what you want. What is the problem? This is this particular region is high values, and this particular is like we can lightly identify, but still we can identify it's a 4 with these 3 columns. But thing is, the columns in the left and right, I mean, the columns which are in the left and right here, in this left and right, are not that much highlighted, and this particular region pixels are highlighted. If you see, the reason is the left and right side pattern, left and right side. If you look at how many times 86 is participated in the competition, only one time. 4 2 times, 8 2 times. How many times it is participated? 184, only one time. So it means the leftmost and rightmost columns are participated in only one time in the computation of this feature map. So that is the reason this left and right columns of this particular convolved image as a what's called less strength, less pixel values, but still we can able to identify the It is a 4. It's a 4 by visually. So image now become 3 columns arranged for 4 column arrangement initially. The image got smaller since we are not moving. We are now moving 2 pixels at a time because of this is the 2 pixels at a time. Okay, at a time. So pixels are getting shared to each and over, but except the pixels are sharing except for the left and rightmost corner element. We have the image smaller and we can still understand that is a 4S. We can understand still it is a so 4 quite a great extent. Also, an important fact to realize is that we are taking 2 consecutive horizontal pixels. Therefore, only horizontal arrangement is considered here. This is the one way to extract the features from the image. We are able to see that left and middle part as well. However, the right side is not so clear. This is because of the following. Because the left and right corners of image is multiplied only once. It is very important. So we are considered this particular element as participate in the competition only once. That is the reason left and right. And also when you are doing this horizontal, when you are using horizontal filter, so you are preserving the horizontal, you are preserving the horizontal arrangement. But what about the vertical arrangement? So how do you preserve this? Or horizontal vertical preserve? So you have to use 2 by 2. So this is horizontal and this is vertical. That's what is next. So we are supposed to use uh, both horizontal to preserve both horizontal and vertical. So you are supposed to use in a 2D filter. This is called the 2D filter. If you look at how this is called one convolution operation. It's another convolution. It's another convolution. If you look at how this convolution operation takes place. Visually I have shown here. That is this is the one convolution. So it has entire convolved entire over image. Okay, you will get the feature map. And the reason for using 2D filter is this a 2 by 2 or 3 by 3 is to preserve the horizontal and vertical space. That is called spatial arrangement. Horizontal spatial arrangement, vertical, both horizontal and vertical. So what we did so far is was that we are trying to extract the features from the image by using spatial arrangement of the images. To understand the image, it's extremely important for a network to understand how the pixels are arranged. This you have to present it. Okay. So this is what exactly the convolutional neural network does. So in convolutional layer, especially the convolutional layer in the convolutional network, extract the features by striding this filter over across the image. You can take the input image, define a weight matrix. This weight matrix is nothing but the filter. And the input is converted to extract the specific feature from the image without losing the information about the spatial arrangement. Okay. So another advantage is, so the here the what is the size? It is the number of columns here is the number of columns here is 4. Here number of columns is 3. Means you are reducing the number of dimensions. So when you are reducing the number of dimensions, definitely the number of hyperparameters also drastically. It means that another great benefit of this approach is it reduces the number of parameters because the number of columns are being reduced. So this is another example of the convolution works. Okay, this is input image and this is a weight map 3 by 3 I have taken. If you look at how this 429 came in the convolved image, when you have to multiply 18 into 1 plus 54 into 0 plus 51 into 1. So like this, you have to do the dot product over this convolved image, you will get this 429. If you look at, if you see here, if you look at what is my stride one, if you look at it now, the numerator it has taken this particular portion for the striding operation. Next, it is taken this particular portion like this. This is called striding one. Okay, here you have straight one. This is called stride one. S is equal to 1. So you are skipping 1 pixel at a time to get the convolution. Okay, to get this value, you are skipping 1 pixel. So you are starting from here like this. So that is called striding. S is equal to 1 means you are skipping 1 pixel to get this next convolved output. So this is made by okay. What is happening in real time when you apply the convolution operation? So when you are applying convolution, this is actual image. So this is image after convolution operation. So it is retaining The weight mat behaves like a filter. Okay, this filter image extract particular information from the original image. So what is meant by striding? Okay, as said, striding means how many pixels that is skipped. So what is meant by padding? So when we have to use the padding, okay. So now if you see, so what is the output image size here? It is 2 by 2 here. So what is input image? 1, 2, 3, 4, 5. 5 by 5. So the input image size is 5 by 2. As I applying of convolution operation, you are getting 2 by 2. But that is what I want. Sometimes what I want, so my input size also should have 5 by 5. But the output size should also have 5 by 5. So when you have to retain the input size image, the size of input image, the same as 5 by 5. Like even after this convolution operation, you have to add some extra like this. You have to add some extra zeros like this. And this is called zero padding. It won't hamper your image because the zero has no significance and so zero means it is it's very least in the what you call in the pixel density as per the pixel density. So it will don't have any impact over the actual image. So when you are adding, this is called pad. This is called the padding. So the padding p is equal to 1 means you are adding one horizontal row and one vertical row. One horizontal row and one vertical column. P is equal to 1 means this is the p is equal to 1 case. You have to add 0 across all the borders. Okay, that is why p is equal to 1. P is equal to 2 means you have to add another layer of. So this is padding. Why we are requiring padding? As you can see, the size of image keeps on reducing as we are increasing stride value. So when you are using SS value, the size of the output image is getting reduced. So hence the padding the input image with the zeros across it solves the problem for us. We can also add more than one layer of zeros around the image in case of higher stride value. So if you ask what is the problem, you will have the same image. If you look at here, if you adding this zero, what is the input sum image? So 1, 2, it's a 5 by 5. If you look at what is 1, 2, 3, 4, 5, it's a 5 by 5. So your input is 5 by 5 and output is 5 by 5. So just to preserve the input size image and output, the size of your output, the convolved output image should be same as input size image. Then you have to use the same padding. That's all about the same padding means what is it? Zero padding and same padding. Zero padding means you are adding the zeros. The same padding means how many layers we have to add to retain your input size image. That is called same padding. So another important thing, so far we are talking about only one filter. So sometimes what will happen, you can also use the multiple filters. So, and this is one important thing. One thing to keep in mind that the depth dimension of the weight, the filter weight means filter should be same as the depth dimension of the actual image. This is very, very important. And the weight extends the entire depth of the input image. Therefore, the convolution with a single weight matrix will result in the convolved output with a single depth dimension. So, what is happened? When you are convolving over, you will have only one feature map with the depth is equal to 1. So, when you are doing the convolution operation, what is the important thing you have to check? The filter depth, the first point, the filter depth should be equal to the image depth. So, when you are doing such convolution operation, the output of that feature map depth is 1. That talks about the second point. In most cases, instead of single filter, we can have multiple filters. This will mean by k value. I discussed what is the k in the earlier case. So in this case, if you talk here, it is a 32 and this is the depth is 3. This is width. So as if you talk, this is width and this is height and this is depth. If you look at the depth of what is the first point saying, the depth of input image is same as the depth of the filter. So what is meant by a filter? The filters is of size. So like this, it is meant by. It means we have a 5, 5, 3. The depth of this and depth of should be. So you have a 3D filter, a 3-dimensional filter, which depth is 3 and width is 5 and depth, height is 5. So this depth should be equivalent. So when you are performing such thing, you will have only one feature map. This is one feature map. But as you are applying 10 filters, you will have 10 feature maps. That's about what are the points I discussed. The same thing I kept in the pictorial manner. So that this should be equal. So when you are performing one convolution operation with this one filter, what is one filter? 5 by 5 by 3. with this one image. What is the image? 3 into 32, 32 by 32 by 3. When you are converting 32 by 32 by 3, when you are applying convolution operation with what is the size? 5 by 5 by 3. This should be equal. And you will get what is the output? You will have 28 cross 28 cross 1. So this you result into only the depth of 1. This is the depth of 1. Okay. So as you, how many convolution filters you are applying? You are applying 10 such filters. So as a result, so for one convolution you will have one uh, stack. So they will have 10 such feature maps stacked together. This is my way. You will have then you will have at the result you have 28 cross 28 cross 10. As you are applying 10 filters over here. So what is the pooling layer? I mean, I discussed all these things. Just I want to visualize and some insights about this pooling layer tutorial. So this is the example. So what is the pooling layer? So first we will divide your cells into some rectangular cells and square cells. So this is one. How many divide? This is one such cell, and this is 1, 2, 3, 4. So what is my filter? This is a. I mean, this is pooling layer. What is the output of pooling layer? If I use max pooling. So what is the max over this? 429, 509, 26, and 7. What is the max? The max is 780. So in these four cells, what is the max? 856. So in this fourth, what is the maximum value? 913. In this, what is the value? 851. So from every portion, you are identifying, extracting the maximum feature, maximum pixel value, so that you are extracting the most significant features. Okay. So you can use 2 by 2 or 3 by 3 also. This when you are applying 2 by 2 or 3 by 3, but this 2 by 2 you can apply without overlap. 3 by 3 can be applied with overlap, as I discussed earlier. Just an example. Okay. How the real-time image you are applying. So there is no much still we are able to identify the image great extent. Okay, this is actual image. After performing the pooling operation, also still we are able to identify. It's still it is a car. Means what we can conclude from even after pooling operation, also we are able to identify important features and ignoring the least important. That is the max pooling. You are extracting maximum intensity pixel by applying max pooling. So definitely you will have most significant features will be retained and the least significant features will be ignored. That will be my pooling operation. So this I think already discussed. I mean, what is the dimensions of sorry, convolution layer and the pooling layer? What are the hyperparametric case? So this is their case the number of filters. If you say that is in this case in our example, it is k is equal to 10. This is hyperparameters. So output layer, and this is similar to the our output layer is similar to our traditional neural network. It will have input layer, hidden layer, and output layer. The activation function here is the radio activation function, and it will use the back propagation algorithm to train these weights, update the weights, the biases by minimizing the loss function. This is it. If I put all together, this is how the CNN look like. How the convolution neural network. This is my input image. This is one convolutional operation, convolution layer, and this is one max pooling layer, and this is convolution layer, and this is max pooling. The pooling layer we are doing max pooling, and this is our traditional neural network. And here we have 10 classes. So we have 10 classes. So that is the reason we will have 10 neurons, and so in this case we have to use which activation function? Software. As an activation function we can use at these neurons. Software activation. So this is a, if you visualize, this is a up to here it is a first block. If I say this is a first block and up to here, and this is a second block. Okay. So same thing. I mean how the traditional neural network. So the output is then generated to the output layer and compared to the output layer for the error generation. How the traditional neural network works. Okay. Look at here. So first you will identify the error, and this error is back propagated to adjust the weights here and adjust the what you call the filters over there. The filters will be there right here. The filter, adjust the filters. The filters, if you want to adjust the filters and the weights at this layer and this layer, we will use the back propagation algorithm. That's similar to our the typical back propagation algorithm in traditional neural network. Okay, and just I want to discuss some more things, then I will wind up. Not CN, I will discuss the CN architectures later. Okay. So if you look at so if you drop out, if you observe here, there is a dropout. What is this dropout mechanism? So what is this dropout? So what is it? Why should we use the dropout? Now, if you look at what is the dropout, it's a simply you can say in layman terms, we are drop some neurons. We are active. We are dropping some neurons. The term dropout means dropping off some units. Units are nothing but your neurons. Simply put, dropout refers to ignoring units during the training phase of certain set of neurons which is chosen at random. So we will randomly pick up some neurons to drop out them. We should what does mean? Those neurons have no more role in prediction of some image. So why should we use it? Why should we use it? We are saying that we are supposed to drop some neurons. Why should we use it? Why do we need dropout? A fully connected layer outputs most of the parameters and hence neurons do develop because of this overfitting problem. If you look at what will happen, so when they will develop a codependency among each other during the training phase, which curbs the individual power of each neuron leading to the overfitting of training data. So what will happen when if you don't drop out, so what will happen? It will develop the codependency among the neurons and it leads to the overfitting. So to overcome this problem, you have to somehow break out this dependency. So that's the reason you have to in between you have to drop out some neurons so that we can break this dependency, codependency among each and every neuron, so we can avoid certain extent the overfitting problem in training. So it's similar to the regularization mechanism. So if you look at how we can overcome the what you call or how do you usually how do you solve this overfitting problem using the regularization, right? So it's a dropout is an approach to the regularization to the neural network which helps to reducing the interdependent learning among the neurons. So that is the reason dropout is necessary. Okay. So this is a standard neural network. So dropout means we are ignoring applying dropout means we are applying dropout on some neurons. It means those will not participate in a training phase. So what happens then how do we then how do we choose which neurons have participated in the training phase and which are not. So then problem occurs in case of testing phase. So this problem can be tackled by how by we are reducing the activation value by a factor of p. In training phase, we don't know how many neurons have participated or how many are dropped out. So we know that P neurons are dropped out. But which are those P? We don't know in train testing phase. So hence to tackle this problem, what they did, so they will connect this activation of all the neurons and it divide by the P. So that it means that by dividing the is factor of P means we are ignoring the activations of P neurons. It means we can, some extent we can. That way we can calculate the testing accuracy, testing results in testing phase like this. So another problem with CNN is vanishing gradient problem. So the solution for what is the vanishing gradient problem? And if you use the more layers, most of the people will think that most layers, if you use the more layers, you will get a good accuracy. It's not completely right. What happens when you use the more layers? So if you have hundreds of layers, it causes the problem of vanishing gradient problem because the activation function, if you use here, if you use the sigmoid activation function, and what is the you are supposed to find out the weights of the filters and weights of the fully connected layer. So what you are supposed to find out is derivative. But when it's but because the derivative is sometimes if you have the more number of layers, it becomes zero. So if you it tends to the zero, it approaches zero in this region. So that is the reason when you are applying the derivative, even if there is a much, what is the function, activation function rule? Irrespective of input, it squeezes the values between 0 and 1. What is the sigmoid activation? What are the value? It is 0 to 1. So when you are applying derivative, obviously there is no, even though there is much change in the sigmoid activation function, so its a derivative have least significant, okay, least the derivative is there is no much change. So what is this derivative significance? It's called what is gradient or the derivative or gradient. The gradient will decide how what extent you have to modify your weights. If there is no much change in the grades, you may not apply the you not update the weights. What is the problem with this? It will take more training time. So if you use if you are using hundreds of layers, if you are using hundreds of layers in deep network architecture with sigmoid activation function, so this derivative becomes zero, small. There is no much change. So hence we cannot train well. We can train it. So for too small training to train effective for effective training, this is not a good. Okay. So that is the reason. What is the solution? The solution for this is rail activation function. The rail activation function is look like this. So, so I don't have time to discuss on the different CNN architecture, but I will put a slide. Okay, so there are different CNN architectures. Whatever architecture you take CNN architecture, the underlying layers will be convolution layer and pooling layer, the railway activation function, and fully connected layer. And in the recent developments they have used, but underlying the basic layers will be these four layers only. If you take any CN architecture which has shown in this slide, okay, the latest one is restless Next. Restless Next is the latest CN architecture for the image classification. It was the invented in 2000. It was developed in 2019. Okay. So the first one is AlexaNet. Before the AlexaNet and AlexaNet and LeanNet is both are almost the same. Okay. So some people say the first no CNN is LeanNet and some people say AlexaNet, but I say it's AlexaNet. Okay. There is no much change between LeanNet and AlexaNet. Okay. Both are almost the same. So these are so many different CN architecture we can say from 1999 to 2019 till last year. There are so many architecture have been evolved in the field of deep learning and CNN especially. So, but if you take any CNN architecture with Inception or ResNet or BCGNet or any network, any architecture, the underlying layers will be convolution, pooling, and railway activation layer and fully connected layer. So that's all about CNN architecture, about convolution neural networks and its limitations is what is the limitations of CNN? Is vanishing gradient problem. How can you overcome the vanishing gradient problem? Vanishing gradient problem. How can the railway activation function? So another is overfitting. How can you overcome the overfitting problem? By using dropout mechanism. It's a kind of regularization mechanism. That's all about CNN architecture. If you have any queries, you can ask. Yes, dear participant, my presentation is over. If now the session is open for the queries, you can ask any queries. I covered what extent I can today for class. I thought of covering CNN architecture also, but time is not perfect. I hope it is clear, and if you have still any more queries, you can ask it.
Thank you, sir. Participants, if you have any queries, yes, you're welcome to ask.
Yeah, thank you, Ramalinga sir, for your informative session and a nice presentation too. Thank you for accepting our invitation and doing the same. Thank you, sir.
Okay, okay. So, thank you.
Yeah, participants are requested to unmute yourself and clarify your doubts with the speaker. Now the dais is open to get the responses to the queries. Okay, someone asking what is epoch? Epoch is iteration, sir. Epoch is iteration like for loop. For loop for 5
So
times. Yeah,
one epoch is including one forward pass and one backward pass. That together is called one epoch.
yeah.
So forward pass means you will do the some activations. I mean, like traditional neural network. I mean, so once you find out the gradient, I mean the error, that error is propagated till your first layer. So that is going forward and coming back to the starting layer, input layer is called one epoch.
Okay. So as you told that if you want to retain the spatial dimensionality of the image, we should go for CNN, right, sir?
Yes, 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 yes,
Yeah.
yes. So if you want to preserve the spatial arrangement, how?
Yeah.
So
Spatial
that's why I shown the example of it. Yeah,
dynamic
definitely, definitely. So that is not tackled by your traditional
neural networks.
neural networks, MLPL.
Which algorithm
Yes,
can be
yes.
used for satellite images? Okay, sir. Satellite means
So
what is
there
the
are so
object?
many senior architectures.
I'm asking first.
Sir,
So, what is the objective of your satellite image processing, sir? Subhashni, sir, so, ma'am, or whatever it is. What is the objective of processing your satellite? For what purpose you want to process? Can you clarify your query? Which algorithm can be?
suppose so if okay,
Yeah,
okay, suppose if your satellites is taking the pictures, okay, you want to classify
yeah.
which portion of the suppose if you want to take the crops image that you take, so which is, you can classify that this is a rice crop, this is a some other crop, like that you can do it based on the one, like this you can also do for the mostly for the classification purpose, or also for object detection also. Suppose there are in a given image there are so many objects, but I am not interested in all the objects. I am interested in a particular object. Suppose there is a group. I am interested in a particular object. So that is an object detection also we can use CNN.
Sir, is there any particular algorithm for that?
No, no, these are all algorithms only. What are the algorithm choice? These are all CNN architecture. You can use any architecture. You can use ResNet, say LXNet. These are all architectures. Okay? You can use any of these. These are all. The basic funda is different, but the number of layers. So if you look at, if I
No,
talk
sir.
about all these,
For a particular identification, object identification, can we apply all these types of
yes, yes, yes,
algorithms, or
yes, yes.
otherwise any specific one?
No, sir. You can use any of this. The only the all these networks, if you take Alexa net, VGG net, Inception net, REST net, so how they differ, that they will differ how many number of convolution layers you have used, or how many number of
Okay.
pooling layers you have used, and how many number of, I mean, what you call it, they will differ in terms of the hyperparameters. What is the hyperparameter? How many number of convolution layers, how many number of pooling layers. But in case of
Oh,
RESTnet and InceptionNet, they are little bit, the basic funda is CNN, but there is a little bit new concept called grouping convolutions. So the slight modification is there, slight little deviation from CNN. The basic is CNN only, but the inside the CNN in convolution, they will use some kind of grouping mechanism in case of inception and in case of ResNet, they will use residual blocks. Again, inside the residual block, if you look at, they will use CNN inside. Again, during the convolution operation. Wherever you go, all these networks, the CN, the convolution pooling, relay activation layers will be there. But the only thing is the way they will they will arrange these convolution and pooling layers is different. As a result, you will have number of hyperparameters also vary. So if you want to go for the less number of hyperparameters, you have to go for the LXNet. If you want to go for more complex network, you go less next. So depends, depending on your problem. If you try it, you just to try it, all these things. There is no generalized algorithm suit for all the problems. For your problem, if some any of this network may be suited. Okay, you cannot say that which algorithm work for which. Unless until you experiment, you cannot come to.
For all queries, only one answer is experimentation because no two datasets
Hmm.
are same. No two purposes are
Hmm.
same. So the only solution is experimentation on your own dataset depends on own your objective.
Yes.
okay, sir. Thank you, sir.
Thank you so much, sir. Ramalinga Swami, sir. Thank you for delivering the talk. So we'll take a break for 5 minutes. Next session is on the topic Essentials of Deep Learning and Applications. This talk will be given by Dr. N.P. Kavya Madam from Bangalore. We welcome Madam Kavya Ma'am to this STTP. So after 5 minutes, we'll start the session, ma'am. Participants will take the break for 5 minutes. Next, we'll start the session. Thank you.
Ma'am,
Madam,
have you posted the attendance link? Actually, I'm attending by phone, madam. I'm unable to see the chat.
no, ma'am, not yet. We'll post at 1,
Okay.
1 p.m.
Okay. Thank you, madam.
Okay. welcome back. Now the session is on essentials of deep learning and applications. This will be given by Dr. Kavya Madam. Before hand over the session to Kavya Madam, let me introduce her. Dr. Kavya Madam, working as professor and HOD, AI and ML Engineering Department at RNS Institute of Technology, Bangalore. And she has 27 years of experience in engineering education and R&D. She published 90 research articles and papers in reputed international journals and conferences, include IEEE, Springer, ACM, and she authored 2 books referred at Louisiana State University, US. Her Google Scholar citations are 124, and highest number of downloads are around 5,000 by international journal Tyler and Francis for the work A Framework for Big Data Pre-Processing. And she acts as BOE Chairman VTU Malgavi and BOS member VTU and various universities and autonomous institutions also. And Dr. Kavya ma'am has 7 research scholars and 3 were already awarded PhD under her guidance. And Dr. Kavya Madam organized 30 technical faculty and student development workshops, 4 national and 4 international conferences. She also had awards like IEEE Best Paper Award for real-time video denoising at Kochi and received Best Faculty Award for Academic Excellence at RNSIT and received Bharat Jyoti Award and Certificate of Excellence for remarkable achievements in the field of science and technology. And she received Glory of India Gold Medal, which was awarded at National Seminar by International Institute of Success Awareness, New Delhi. With this list of achievements, I would like to welcome Dr. Kavya Madam to this STTP. We welcome you, ma'am. I request you to take over the session and continue, ma'am.
Yes, ma'am. Am I audible, ma'am?
Yes, ma'am.
Allow me to share the screen.
You can share, ma'am.
Okay, is it visible, ma'am?
Yes. Yes, madam.
Fine. So thank you for that wonderful introduction. And good morning, participants. Today, I'll be delivering a session on essentials of deep learning and its applications. Ma'am, my voice and the screen, is it fine?
Yes, madam. Fine, madam. You can continue.
So myself, I'll be taking you across the different issues in deep learning and also a little bit of applications of deep learning. So let us start the session. Participants, can you look at the screen? Can you recognize who is this? Unmute yourself. You can talk to me. Yes, this is, if you just look at this, you can make out it is Aishwarya Rai. Most of you probably, yes, you got the point, right? So that even without showing you the complete image, your mind was able to make out. You could recognize the image and you could say, yes, it is Aishwarya Rai. This is one, interesting thing with the way our mind is going to cognize when you see things, when you, capture images with your eyes, record it in your brain, and there is a long process inside. I'll sail you across the deep learning concepts with these issues. Something went wrong. We started with something like this, and again, we are back to the same position. What's the most powerful problem solver in the universe? So we say that something like, well, the very first thing is your human brain. Okay. And this was proposed by Douglas Adams. And you know how the very first invention of a machine was a wheel. And the second important problem solver in the universe started with the evolutionary mechanism proposed by Darwin. These building problem solvers will be something like mimicking. See, there is something called as mimic, there is something called as copy. These are two different things. There's a major difference between mimic and copy. Fine. The very first thing is that when you say you're going to mimic, it is like you're trying to duplicate, you're trying to replicate. When you say you're trying to have a replication of something, and that is what neural network or artificial intelligence is circling around, the concept of mimic. And the concept of copy is just have a Xerox, just have a direct, duplicate of it. When you replicate, we call it as mimic. When you try to assert the characteristics in the model what you're going to build, we call it as mimic. Whereas when you try to have a direct copy of it, when you duplicate it, we call it as, it is a copy character. The complete concept of a neural network, the complete concept of deep learning is more of mimicking the human brain. The human brain can be conceptualized as the neurocomputing process, and the evolutionary mechanism, whatever we say, we can conceptualize that as evolutionary computing. Now, we have arrived with two types of computing. One is the natural brain and the concept what happens in the neural network of our brains. We call it as neural computing. And the other part is evolutionary mechanism where data is being evolved from technology is being evolved over years. When you have something called as technical classification of your computational intelligence, we call it as a taxonomy. What is taxonomy? The technical classification of your intelligence here. Inside this area is what we are going to talk about deep learning. The neural network, evolutionary mechanism, and fuzzy systems are the three major computational intelligence or soft computing methods. And we just discussed the neural network is a brain-like representation. Evolutionary mechanism is the concept which is being evolved, and fuzzy is something like when you're not confident about your input and you are thinking like how it could be a positive, a negative, a true or a false. You're good or bad. What is your answer? You say maybe I'm 50% good, 50% bad. When you try to make a compromise between good and bad, true and false, 0 and 1, and not sure about it, you get into another major stream of intelligence which we refer as fuzzy systems. Now, evolutionary algorithm is our focus. Most of the time, we'll be talking about programming, strategies, algorithms, and genetic programming. Everything is based on performance, wherein it should be acceptable with the available cost with a wide range of problems. When you have intrinsic parallelism, it is more of robustness, fault tolerance, and we have more complex problems wherein we have a lot of data getting into the system, and then comes complex relational parameters and local optima, which leads to a field of deep learning. Hard computing and soft computing, we have precise and approximate models. So in precise models, symbolic reasoning, traditional numerical computing, and approximation model, we have approximate reasoning and functional approximation with randomization representations. Getting into our area of machine learning, we know that humans learn from past experience, which we refer as a component E. And computer follows instructions, wherein we try to write the algorithms and we try to write the mathematical representations. We try to give experience in the form of data to the computer, and we try to make the systems learn to prepare itself for certain action. This is a basic definition of machine learning. We'll get into in detail. Our area is more about neural networks. In neural networks, probably in the beginning session, you've already discussed the meaning of neural networks. A neural network is massively parallelly distributed processor which has got natural storage representations, wherein we have different layers like your input layer, output layer, and your hidden layers. Now we are trying to resemble the human brain here. That is the most important issue with your neural network. We're trying to acquire knowledge in the network, Okay, we call it as knowledge acquisition process. And this acquisition of knowledge happens through a process called as training, which is also referred as a learning process. The interneuron connections forms the strength, and we try to associate weights to store the knowledge. If you look into the multidisciplinary view of neural networks, this is how it looks like. Computer science and artificial intelligence is a major contributor to your neural networks. We have mathematical approximation algorithms. We have physics with dynamic representations and statistical layers, economics, finance, engineering, philosophy, linguistics, cognitive psychology, neurobiology. All these are different domains of your neural networks. Where does your deep learning start? So artificial intelligence is one big domain wherein your neural networks appears, and within that we have got the concept of your deep neural networks, deep learning. To get into deep learning, first of all, let us understand the meaning of artificial intelligence. Now, if I just talk about deep learning, what comes into our mind? Or before entering into deep learning, let us talk a few seconds about artificial intelligence. Now, we have a different perspective here to represent artificial intelligence, which is explained in a very simple way. I'll take an example of ourselves, human beings. Human beings, we have the capacity to speak. This concept or this area of artificial intelligence we refer as speech recognition, wherein we have statistical learning also. Human beings can read and write. We read and write using different languages. This area of artificial intelligence, we refer that as natural language processing, or the NLP. We see through our eyes. Our eyes will recognize the scene. This is an area of computer vision wherein symbolic reasoning happens, and symbolic reasoning and computer vision are also an area of artificial intelligence. When we see anything, we try to recognize. Okay, we recognize the scene. This is an area of image processing. Eyes and mind are interconnected. When you see something, you recognize. This issue is called as cognitive capabilities, which happens in the brain, and that is our area of neural networks. The brain has got a basic thing called as a neuron, which is a core component of a neural network. The neural network will have complex data in it. Thus, when you have to handle complex data with neural network, there comes our area, deep learning. More the knowledge, more is the data, more are the hidden layers. Now, whenever you scan an image, fine, from top to bottom or left to right, we recognize the object, and that issue is called as a convolution neural network. You had a session on convolution neural network, CNN, just now at 9 o'clock. Probably you have learned in detail. Similar to that, suppose I ask you a question, what dinner did you have last night? Few of us, at least some of us, will remember what we had last night for dinner. That is, you're trying to remember the limited past. That is an area of recurring neural network, RNN. CNN and RNN are two major areas of neural network which has got cognitive capabilities, and in turn we have got something called as deep learning in neural networks when the data is pretty complex. Now, as it is, artificial intelligence can be broadly classified into two areas wherein you want to solve the problems. If it is symbolic based representation, okay, like how humans see the data and we can see in one dimension, we can analyze 2 or 3 dimensions at most. Beyond that, humans cannot, have a computation method for recognizing objects and doing computations. That is a symbolic based representation. The artificial intelligence works in another category other than symbolic based, and that other category is database type of representation. If it is a database type of representation, there comes our area of machine learning. Unlike humans, in humans it is only 2 or 3 dimensions, whereas in machine learning the machines can understand more than 2 dimensions. They can understand even 10, 15, 20 dimensions, which a human brain can never even think of analyzing. And this machine learning again is characterized into 3 ways: supervised learning, wherein the data is labeled; unsupervised learning, where the data is not labeled and you want to try to derive the data; and the last type of machine learning method is your reinforcement learning. We'll get into machine learning methods when we talk about deep learning in detail. So about artificial intelligence, these are the things I wanted to tell you. We can understand AI in terms of humans. Either it could be vision, it could be computer vision, it could be CNN, it could be RNN, it could be speech recognition, it could be NLP, and it could be even your image processing and pattern recognition. So with this introduction of artificial intelligence, let us go further. As I told you, machine learning is a type of artificial intelligence that provides the computers to learn explicitly programming representations. You have got the label data, you have got different machine learning algorithms, and when you train your model with the available data, we try to make prediction out of it. Doing predictions is one strong area in unsupervised learning methods. Now, what is deep learning? A part of machine learning. Deep learning is an area of machine learning wherein, again, in turn, it's an area of neural networks. AI leads to NN, neural network representation. The neural network will be mimicking our brain, and then from there, we have got another representation called as your deep learning. So we can refer this deep learning as a part of machine learning, wherein you're trying to utilize the different algorithmic representations to mimic the human brain. One standard representation could be the hierarchy type of representation. When you have tons and tons of data with multiple dimensions, there is a place where your deep learning, pitches in. What are the different applications of deep learning? Google in 2011 launched the Deep Learning Focus project. In 2014, it bought a concept of DeepMind with AlphaGo. Microsoft speech recognition translation is one standard application. And in Facebook, translating the user post for more than 40 languages is one major application of deep learning. Baidu is a speech recognition and translation for photo search and for self-driving cars. Our deep learning is inspired by the brain, how our brain works. The cognitive sciences and the neural network representation is an inspiration for our deep learning representation. Our brain has got a lot of neurons which are connected to each other, and these connectivities and the mental representations in our brains have led to these algorithms. This is one small screenshot which shows how our actual brain representations are. You have a nucleus and the axon dendroid here, and this is the way it is equivalently represented with the activation function and with the weighted connections. Why deep learning? The different applications, as I just now mentioned, the speech recognition, the computer vision, natural language processing, these are the 3 major applications of deep learning. Look at this diagram. We have different layers here. The initial layer, we call it as the input layer, and this layer is called as the output layer. Now, let me explain how the concept or your deep learning representation works. To start with, the first thought of deep learning, when I say deep learning, what strikes in our mind? The very first example we can think of is the Google translates the entire web page content from any language to any other language in a matter of seconds. I'll repeat. Google translates the entire web page content from one language to other language in a matter of seconds. That is deep learning. Your phone gallery groups the images based on the location. Your phone, what you have on your mobile, that can group images based on the location. That's also a product of deep learning. Now, what exactly is deep learning? Deep learning, I can say, it is a subset of machine learning, which in turn is a subset of artificial intelligence, wherein artificial intelligence, you're trying to mimic the behavior of human brains. Machine learning is to make algorithms which are trained with the data and are intended to get some output. Deep learning is a domain of artificial intelligence which is inspired by the structure of the brain. In terms of deep learning, the human brains are mimicked in the form of an artificial neural network. We call it as ANN. Deep learning, how is it different from machine learning? If we create a machine to differentiate between tomatoes and cherries, let's take an example. I'm trying to give you the difference between deep learning and machine learning in simple terms. If I want to have a machine which can differentiate between tomato and cherry, then if I use a machine learning representation and ML algorithm, I'll try to give the data about the features of these two items. I can say size of tomato, size of cherry, type of the stem in tomato, type of the stem in cherry, the color. Like this, I try to make the features in machine learning algorithm. If it is deep learning, the deep learning features are picked up with a neural network without any intervention of the human input data, which can handle huge amount of data to train the machine. I'll take another example. Now suppose I have 3 students and I'll ask the 3 students to write the digit 9. Okay, I have 3 students. I'll ask them to write the digit 9. 3 students write it in 3 different ways, but humans, we can recognize that all these 3 different ways it is number 9 only. How about machines? When they are trained to write 9 in one way, and you have to recognize the number 9 written by 3 different people in 3 different ways, that is what you can think of deep learning representation. What happens in a neural network with this example of writing 9? Use a neural network and train that to identify a handwritten data to represent the number. For the number 9, what I do? I take a 28 by 28 pixels across my x-axis and y-axis. That 28 into 28 will now be 784 pixels. And then the neuron, which is a core entity of the neural network, okay, what you can see here in the diagram, every cell is a neuron. This neuron will start processing each of the 784 pixels, which is fed in the first neural network layer. This 784 is fed in the first hidden layer. Now this becomes your first layer, becomes your input layer, wherein the input is fed. And at the end, we have to reach the output layer here. In between, I will have these hidden layers. Working of your deep learning, the information here is transferred from one layer to other layer, okay, through the connecting channels in between these lines. We refer them as a connecting channels, okay, and each of these will have a value attached to it, and we refer those values as a weighted channel representation. All the neurons will have these are the channels, and these neurons will have unique number associated with them called as the bias. The bias is added to the weights, okay, which is activated for every neuron. You have the bias on these channels and you have the weights, and accordingly they are activated to the further layers in the neuron. The bias is added to the weights, which will activate the neuron through the activation function. Now we have 3 things. We have the weights of the neuron, we have the bias value, and now this neuron, whichever other neuron it is going to activate, for that I have got an activation function. Now we have got 3 components: weight, bias, and the activation function. The result of the activation function will lead to a particular neuron is activated for one particular channel with the bias and the activation function. Some particular neurons in this hidden layer will get activated, and the activated neuron will pass the activated information across the different layers. These neurons, whichever are activated, will pass the information across the different layers in the network. The weights and the bias are continuously adjusted every time to produce the output in a well-trained data. Every time we have to adjust, okay, the weights to get a well-trained network. Now, with this introduction to your deep learning, let me also tell you how deep learning is applied. Simple example like customer support. Okay, I have bought an item. I need a customer support. I'll talk. I'll ask. I have bought a new television. I'll just make a call to the customer support and I'll ask, can you just explain me how is that I'll dismantle this television and get it connected to the internet? At the other end, there's someone talking to me, and it could be a bot. Deep learning is one strong representation concept used wherein we have bots to reply to the customer. The customer support calls are taken care of by the bot, and when deep learning concept is used, the customer in this end will not even know that it is a bot. In the other end, talking to him. Similar to this, other than customer support, medical images detection, detecting cancer cells in MRI images and giving a detailed report is one standard representation for medical field. Using deep learning, it will give a detailed report on this MRI images to detect cancer in certain stages of development. Automobile is one crazy area of deep learning wherein we have the self-driving cars. Apple, Tesla, Nissan are few of the companies who have started working with this automobile self-driving cars using the concept of deep learning. To go further, what has changed? You can see here, old wine in new bottles. The big data and the digitization led to deep learning. Other than digitization, the computation, the speed, whatever is required has also led to deep learning. And here you can see the concept of Moore's law and GPUs. What do you mean by a GPU? I'll take a pause. Can anyone of the participant answer? What is a GPU? All of us know computations are done with CPUs, right? What is a GPU?
Graphical
Graphical
processing
processing unit.
Exactly. Now that it is the second day of your FDP and you've already studied, CNN and all that, probably very good. Graphical processing unit is one major computational representation which has pitched in. And also we have this algorithmic progress, that is the algorithms would have been designed. What we say old wine in new bottle is that big data representation, digitization, computations with your GPU and Moore's law, as well as algorithmic progress. That is the change which has happened with your deep learning. Now we will be doing a little bit of feature engineering in your traditional approaches. You have the input data, you have feature engineering here, and this will cost us a lot of time. Now, what do you mean by feature engineering? We'll have a look at feature engineering because that is how we try to get into deep learning. We try to avoid this concept of feature engineering, which is taking lot of computational time and space. We'll directly input data to deep learning network, wherein this feature engineering is taken care built in your deep learning representation. So the feature engineering, whatever we had earlier, we will look in detail and how deep learning has taken over this entire traditional algorithmic approach to fasten the process for big data and fast computation is one beautiful area of your deep learning. Let's take this example wherein I've got a sample data. I'm trying to do a prediction. We can also have two methods here, like your feed forward representation and your feedback or your back propagation representation to update your network with different weights. We try to make the system learn with some error also associated with it. Now, we always try to readjust the deep neural network with the weights. We readjust the weight to get a better accuracy. So let's see who is that we do. This is the first thought, examples which I've already quoted, wherein the Google translates the entire web page or your phone gallery, which will group the images. That is a concept of deep learning. And exactly what deep learning is, it's an area of machine learning. These concepts I've already told you. Okay, we'll get into this. Where it is applied, I just told you. Okay, what exactly is deep learning? The first thing, and. Why is it generally better that other methods like speech, image, and certain other types of data also you have, then how deep learning will take care? The short answer or the crisp representation of deep learning could be something like that. Deep learning is a neural network, but there are several layers and nodes wherein we have an input, output, and a hidden layer. This is one short answer. Or we can also put it like the series of layers between input and output, wherein we have feature identification and processing through different stages of the network, and we try to have our brains working with it. That is a reference, what we can say for your deep learning. These two are the short answers for your deep learning representation. To go ahead, we have something like multi-layered neural networks which have been around for 25 years. And this is not new. Multi-layered neural network was already there. And what is being added to this to get into deep learning concept? What is new here with your neural network representation? We always had good algorithms for learning, wherein we had weights in the network. We also had hidden layers. Those algorithms were not good enough in learning to have the weights in the network to getting, to have them, the readjustment mechanism and all that. Right? So what is new here? The later networks, what we have in neural networks, the later developments, what we had other than the regular feature extraction is about deep learning. Now, what do you mean by later networks? If you get into the longer answer, other than short representation of deep learning, if you have a quick explanation or if you have a reminder on the neural network wherein the weights are getting learned, the weights, whatever you're going to have, you train the weight also, then that's a new concept. Okay, that's what deep learning talks about. And the idea of unsupervised feature representation, wherever we have these intermediate features and the neural network naturally learns, but you cannot have the goal not being known. In unsupervised learning, it is that the labels are not known or the goal is not known, and you try to determine the features. That there also we have the concept of deep learning. For example, if I want to predict the celestial objects in the space and I want the network to decide on its own what is that object type, that is neural network. But if I already have given titles to the celestial objects and I give the features and I say this type of features are this object, the other type of features are another object, if I have already given everything like that, that is the concept of your supervised learning method. For unsupervised, wherein the label is not known and data is dynamically being handled, neural network as well as your deep learning is answered. The breakthrough out of all these things is a simple trick of having the deep learning network itself trained. You train the deep learning network to answer all these things. Now, how is it? It works. Mathematical representation of your deep learning process. I have, as I told you, in the network, I said these are the nodes. Let's assume the nodes are like this, 0.06, 2.5, 1.4. The weights are given as an input to f of x. F of x is the activation function, and here I write a representation 1 divided by 1 plus e to the power of minus x. Let's see how it works. What I do is 0.06 into 2.7 plus minus 2.5 into 8.6 plus 1.4 into 0.02. This is my summation, and this I can take it as an example of my function, and the result is 21.34. This is just an example for your activation function. You can have different mathematical representation inside f of x. How does it work? This is the data set. The data set, I have got these fields 1.4, 2.7, 1.9. Similarly, the second record, I have got 3.8, 3.4 and 3.2. Let's assume I have already got a class here. The first record leads to class 0. The second record leads to class 0 like this. Now, let's assume I have got a training network like this. And when I give a data to this, when I want to train, I'll initialize the nodes with a random value. I'll say 1.4, 2.7 and 1.9. What is the answer I expect? Out of this, I want this to derive 0 in my output node. But then I'm getting an answer of 0.8. That depends on the function, that depends on the weights being adjusted in the network. I have got a value 0.8. What has happened in between? I have got an error. See, I was supposed to get 0. I have got 0.8. What is the error? The difference between the actual class value and what value I have got in the network, that we call it as an error. Error is one major component which you have to consider in the mathematical representations of your deep learning formula. So to get this, what I do is I readjust the weights. I go back in the network. I got an error in the output network. I readjust the weights like this, and then I again readjust. Let's assume
Participants are requested to mute yourself. Hello.
you can see another example here. I have got 6.4, 2.8, and 1.9. This has led to a class 1 here. Now let's see if I've got a class 1 here. No. After I have randomized this network, I have got answered as 0.9. What was the answer you expected? I expected 1 as my class output, but I have received as 0.9. What is the error here? The expected value 1 minus the value 0.9 is called as an error. So the error, what I have is 0.9 minus 1, the error is minus 0.1. Again, I try to readjust the weights here to get a result 1. The error minus 0.1 is readjusted to get a result 1 here. It goes on and on like that. Whenever you have multiple layers, you try to repeat this 1,000 times or even million times. Each time you try to randomize the training instances and you try to make adjustments in these internal layers, and you're going to try to minimize the error to have a well-trained network. You're designing algorithms here to readjust the weights to have a well-trained network, and our goal is to reduce the error. So there are different perspectives here. What we do is the decision boundary perspective, we call this as, wherein I have got the initial random weights. I'll be, in case I want to give a representation, these are different set of nodes, and I try to randomize that. This is one representation. I readjust the weights. I make instances for the training data, and I'll readjust the weight, and I'm going to change my boundary to cover maximum like this. Yellow on one side, I want the blue on the other side. For that, I'm trying to have a boundary perspective. I again readjust the weight, and I readjust until I reach my goal. I recenter the weights there, and finally I get a representation like this after doing a readjustment. Now look at this. Here, I don't have one line. If I've got one straight line, that becomes a linear function. Now, this is not a linear function. A non-linear representation also you can have to make a decision boundary perspective in your neural network. What is that I'm trying to make? The point I'm trying to make you understand is that the weight learning algorithms in neural networks will be dumb. Okay? Dumb in the sense they are not aware of how much data is being trained and how much they are focusing towards the result. So until I get the result, I go on training the data, I go on doing the readjustment. Because it is a machine learning method, you can do it. It's not done manually, right? You can do it even thousands and million number of times. While you do these adjustments, you're trying to make the network better and better to get the pattern. And sometimes, without your knowledge, it can happen worse in other cases also. Now, what is this dumb? Because it's not known towards where you're going. We call it as dumb luck. Eventually, it tends to get a very good result, and it becomes an effective classification in your real-time application. Okay, so in case you're focusing towards the result and you have got a very good result out of it, we call it as a luck has turned to be there because you're intended to have, and the classes are labeled, and you have potentially got a better result. But then you will have to go further for accuracy. What happens is we'll have in detail a standard neural network wherein the weights are given to the learning algorithm. We will have a function f of x which could be non-linear in its representation, and the network with one hidden layer can also be present, or you can make it more perfect with more hidden layers. A set of weights are always existing, which will be targeting towards the output from the input. And the problem is to find what is the weight adjustment you have to do to get a better trained network. We think it in this way. If you have a neural network with a linear representation, if the function f of x is linear, now the neural network, you will have only one straight line like this. This is a very simple decision boundary representation wherein you don't need many layers here. Later, if it is a non-linear representation, look at this, it will have complex boundary representation. Even though the data is not changed, the boundary altering the adjustment is more difficult. If you go for support vector machine type of representation, okay, that works with straight lines, and also when you transform the data first, it will look something like this in your support vector machines with a linear representation. Now, multiple layers make sense. How is it? Look at this. Look at our brain. I initially told we are trying to make the neural network work like our brain, isn't it? We are trying to mimic our brain. We want the neural network or the deep learning system to work similar to how our human brain is going to work. So this is how our human brain is. You can see you have optic tract. Here you have got different layers, 1, 2, 3, 4, 5, 6, 7, 8 associations and all that. Now, see, my neural network. I have got multiple layers. Okay, I'll make an architecture out of it, and I'll try to have the feature logic to generalize that. Okay, but if it is like this, a linear representation, fine. But if you've got all combination of networks like this, boundary problem and all comes, okay, maybe it does not work efficiently. Then I get into deep learning. Until here, it is only neural network, input layer, output layer, and I've got hidden layer. But if the layers are like this, can I have a direct linear function for this? I cannot. Now, the ordinary neural network, the layered representation doesn't work. I have to get into this type of representation. I go for deep learning. In deep learning, what happens? I'll take it like a neural network only initially. Okay, for better understanding, a new way to multi-layer network looks like this. For our understanding, it actually happens like this. This is the first layer, the activation function, fine, the weights and the bias, everything are carried, and only some of them are activated, and that enters the second layer. The ones which are activated carry the information to the third layer. And again here, the activated values are carried to the final layer. And lastly, we have got the output layer reading here. Can you look at this? I have got all the layers built in my multi-layered representation. Now to do this in our deep learning, what we do is, each of the non-output layers, we train that using an auto-encoder. Okay, using an auto-encoder, I try to train my network. And this auto-encoder, how it works? The auto-encoder, normally, if you can see, you could have studied your concept of encoding and decoding, all that, right? Probably in different subjects which are related to artificial intelligence, we would have studied the concept of auto-encoder and all that. So you can see here, you have the concept of auto-encoder and decoder being represented for multiple layer representation. An auto-encoder will be trained with absolute standard. You try to do the weight adjustment for this, and you try to reproduce the data. Between the input layer and the hidden layer, we encode the data, and between the hidden layer and the output layer, we decode the data. Okay, encoding and decoding will try to happen here in the neural network representation. By making this happen with many fewer units, okay, we try to focus on the hidden layer and the algorithms, whatever we want to implement in these hidden layers using your autoencoder and your autodecoder representation. The intermediate layers here are trained with your encoder-decoder representation. Let us assume it looks something like this. The final layer, whatever you have here, will always try to predict the class from your previous layers. That's it, what I wanted to say with your neural network and your deep learning. We'll proceed further with more applications in deep learning. The basic idea you have already understood, the neural network, the deep learning method, when is that deep learning is going to happen, the different types of autoencoder representation. You can also have variations in architectures for your training algorithms, and this is a very fast growing area. You can see here the input, hidden and output layers make a lot of sense here for your data. The different applications now with your deep learning representations. Just go through this slide. You can see here, Google in 2011 launched the deep learning representation. In 2014, we had the DeepMind, Microsoft speech recognition and translation, Facebook transferring user posts in more than 40 languages, and Baidu is a speech recognition, and also photo search and your auto-driving car representations. Now we'll get into system. We had hand design programs and the output. Classic machine learning representation, wherein the hand design features, we map it onto some features in your database, and then we try to get the output. But in deep learning, it's a symbolic representation. You can have the sample features, you can have additional layers, you can abstract the characters inside these hidden layers, and then you can have a mapping done onto the output. Look at this. This example is to bring clarity onto your understanding of deep learning. You can see here, there is a woman here, okay? This is visible, fine? This is a visible layer. I say this is the input pixel, input layer. The first hidden layer will calculate the edge detection in my first hidden layer. The second hidden layer, I'll try to identify the corners, okay, and contours in my second hidden layer. The third hidden layer, I try to capture the objects, and then in the output layer, I try to get the object identity, whether it is a car, whether it is a person, whether it is an animal. This slide speaks about if I have a visual layer like this and I have an output, you have to determine whether it is a person, how the different layers are processed with your image processing representation. Initially, edges, second, corners, the third one, object parts, and finally, the object identity. When I say deep learning layers, this is how you have to understand. So to get in detail, the lowermost layer will be like this. Fine. The middle layer looks like this. The upper layer is targeting towards the object. In a neural network representation, normally input, output, and hidden layer. But deep learning, it could have a non-linear activation function. As I told you, if it is linear, you have a direct distinction. Okay. In non-linear, that example of that yellow and blue color circles I showed you, that is your non-linear activation representation. The neuron can be used to connect every input across the different layers in your multiple layer, wherein you'll have millions and millions of neurons, and then finally you need to have a proper computational function there for these neurons. What is the drive behind this deep learning? What drives it? The faster machine access with your core representation, core computing, with your CPUs and GPUs being replaced. The big data representation, wherein the data set is very huge, data is large, data is complex, and the new modeling and the new representation of algorithms, all these are the driving factors of your deep learning. More onto deep learning. Here you can see how do you train the deep learning data. You can see here there are different animals here in the input layer. During the training phase, the neural network is fed to thousands of labeled images here. The animals are being classified here. The input, I say it is a dog, okay? The dog is not labeled. I don't have a label on this, but I'm trying to have a network representation to identify out of so many animals that the object input is a dog. The first layer, what it does is the neurons will respond to simple shapes like identifying the edges. Next, in the next hidden layer, I can have with a complex structure like other than edges, hand, leg, head, okay, and different angles, okay, like that. And then in the topmost layer, I'll have the neurons to respond to this complex representation, identify all possible objects which will have features like this, a face like this, a leg like this, and the corners like this, bone like this. So with this, I get three type of objects: a fox, a pig, a rat, and sorry, a dog. Like this, I get three different objects in my topmost layer. Finally, the object recognition or your output, the network should be able to predict the object which is most likely to the training data. Here I've got a dog and I've got a wolf. So finally, I say with all these feature detection, it is mapped onto a dog. Dog 90% prediction and wolf is 10%, which in my neural network, a well-trained network has done a very good prediction here. The neural network, with its remarkable ability for driving with the different patterns and detecting representations, with a capacity of adaptive learning, with a capacity of self-organization, and with a capacity of fault tolerance, everything together leads to your deep learning representations. Now, implementation with your deep learning, we've got something like your cloud with your big data. Your providers could be with Google, Facebook, Amazon, Baidu, and Tencent. The PC implementation with your Linux cluster with your GPU servers using TensorFlow, Python, Keras. These are different ways you can do. And this is a sample how it looks, your GPU cloud, a screenshot. The different deep learning softwares, if it is CPU based, if it is GPU based, this slide speaks about different ways you can implement deep learning algorithms using all these. The basics of deep learning, we have just discussed how deep learning works, and then we are trying to have our thoughts embedded into the vector space and transforming these thoughts with your convolution neural network or your recurring neural network. All these will be the areas wherein you're trying to mimic the human brain onto the system. So usage in your deep learning, essentials, you need to know the usage. Where is it majorly used? When the data is very large and the data is quality is very complex, you go for deep learning. And when you want measurable representation with a desired goal in a defined cost, or it is the computational power which matters, I go for AWS GPU type of instances. Then I go for your deep learning type of representations. These are the different tools. The world's best hardware with a 4 GPU is your Digits Daybox. This is another GPU, okay? The convolution, fully connected convolution represented with 5x representations. And AI and deep learning applications. See, the topic which I started was with essentials of deep learning and its applications. Next 5 minutes, I'll be speaking about the different applications in deep learning. Trend prediction, one standard application. What is trending these days in different customer areas? You say, I want to put up a shop in a very trending area wherein people will buy that product. That is your trend prediction. Understanding the social behavior, understanding what people try to buy online, because it's now pandemic. Pandemic has made the world upside down. There is a trend to be identified before you set up your market. Trend prediction is one major application of deep learning. Recognition, obviously. Cognitive sciences led to deep learning. You have the concept of cognitive representation. I see the person for the first time, my mind is going to cognize. I see the person for the second time, my mind is going to recognize. Recognition capabilities can be built inside the deep neural network. New knowledge I want to embed, making sense of the knowledge, whatever I have, and replacing a complete human with a robo or a bot. That is the area where deep learning finds its intense applications. More applications, each one of you, if you are, some of you are students, can do projects in these areas on information retrieval with your search engine concept. It could be the pattern recognition, audience targeting. Okay, I have a group of people. I want to see how many of you are interested in Airtel, how many of you are interested in Vodafone. I want to, have a list of audience and targeting towards your business. Sentimental analysis on your written text. I want to see the sentiments on your text. See, sentimental analysis is very, very trending. I'll give you an example. When I have a text, I want to understand the emotion. Smile, you can understand. Crying, you can understand. Sad face, I can understand. Fine. Can you capture a lie? Can you capture sarcasm? Sarcasm. I'll give an example of sarcasm. I want to say, oh, you're very good, is it? Oh, I didn't know that. What does that line mean? Are you trying to say you're not good? Or are you trying to understand he is good? What is it you're trying to say? That is sarcasm. Capturing sarcasm is a very difficult sentiment. Lie. I say, I know. I say, no, I did not know. How do you capture a lie? It's impossible to capture a lie. That is one way wherein you try to capture. And other than that, sentimental analysis, a lot of things are there. These two examples are rare examples which people might have thought or not thought of, I try to tell. Otherwise, sentimental analysis is all about simple as when I buy a Coke, I'll also buy a popcorn, right? When I say Coke, you also say, yes, I'll also buy a popcorn with it. So what goes with what? That is sentiment. Finally, you've got the personalization, automation, NLP, social media mining, organic search, and then branding. All these are different applications in deep learning. To continue with application, they said speak on application. These are the different areas. Language translation from one to other. Your Google page does that. Within seconds, everything is translated from one to other using your deep learning methods. Speech recognition, handwriting recognition, face recognition, object detection. Autonomous driving is one standard trending these days. Autonomous driving cars, self-driving cars. As I told you, your Tesla, Nissan, Apple are already there with the autonomous driving cars, generating art, they say, and a few of these like music and photos are also trending with deep learning applications. Now, power systems, people who are in electrical engineering want to work a deep neural network for peak load forecast, failure prediction with your battery, condition monitoring. These are the areas of power system where deep learning is used. Data centers to increase the efficiency of your storage by 15%. And also we have got different sensors, temperatures, fans, windows, identifying the variables for the sensors and managing in data centers. That is one great area of deep learning. Now, there is one small thing I want to mention in my lecture. See, deep learning you have learned with convolution neural network, fine, recurring neural network, fine, supervised, unsupervised, everything. There's one thing here called as deep reinforcement learning. That is also deep learning, okay? When I say neural network and when I say ordinary machine learning method, this is quite simple. Look at this slide. I say supervised learning. This slide speaks about CNN and RNN. As I told you, if I have got an image, read the image top to bottom, read the image left to right. Okay, that could be done with your symbolic representation or your convolution neural network. Then if I say, what did you have last night for dinner? You try to remember the limited past. So capturing the limited past is your recurring neural network, RNN. Now, to get into the details of these supervised learning, now if I say, okay, you have to identify your friends, and the picture of the friend, the name of the friend is already given to the neural network, okay, so it will say this friend with this name easily identified. That is supervised learning, fine, because the names are known and the friends are known, the known data, labeled data, supervised learning. But identifying the objects in the space, and I don't tell Okay, what object is what? I want the machine itself to identify. I want the machine itself to give a name for that and give a representation for that. That is your identifying celestial objects in the space is an example for unsupervised learning, and also it is an auto encoder type of representation. Fine. So reinforcement learning, a very, very trending representation is your reinforcement learning. So reinforcement learning, other than the example what is cited on the slide, I'll give you another example. If you want the robot to climb the wall, trial and error, once it will climb, it will fail. You will tune the parts of the robot. You'll make the robot climb again the wall. Again, it will fail. Again, you'll find out something is missing. You'll retune the robot. Like that, you train the robot, make it climb the wall till the end, and then come with a solution. That is reinforcement learning. Making the robot climb the wall with a trial and error process is reinforcement learning. I'll give you another example. In reinforcement learning, we say something called as Q learning. Q stands for quotient. Okay, or there what happens is, let's assume, okay, I stay in Bangalore. Bangalore is very popular for traffic, to come from my house to college. When there is no traffic, I'll take half an hour. Okay, it's hardly around 10 kilometers. I'll take half an hour. Now in peak traffic in office hours, I take almost 1 hour. Let's assume I'm in my place, my college, RNSIT is in Rajarajeshwari Nagar in Bangalore, in Mysore Road. Okay, from Mysore Road, I have a meeting in Whitefield. Okay, I have a meeting in a company. I'm a corporate consultant. I have to attend the meeting. I get a call in the afternoon. It is 12 o'clock. They say, ma'am, 1 o'clock you have a meeting. Please make it. You have to come here. I have only 1 hour time. Now to reach from Bangalore, Mysore Road, okay, I am in Rajarajeshwari Nagar to Whitefield. Normally, it will take, if it is a normal traffic, I need at least 1.5 hours to travel. There are major routes, okay, to reach from Rajarajeshwari Nagar to Whitefield. If I take the regular way, wherein the shortest path, okay, but full of traffic, I will take 2 hours to go. If I take the longer route, outer ring road from Rajarajeshwari Nagar to Whitefield, outer ring road, it is double the distance. Okay, the path is lengthy. It is not shortest path. It is the lengthiest path, but low traffic. Okay, I may reach in 1.5 hours. I may reach in 1 hour. Now here I am putting a constraint on my network. I say you take the longer path. The constraint is you have to go in time. The time is less. You reinforce a constraint called as time in the network. I am satisfying only time. It is not the cost. It is not the path. It is not the distance. It is not the space. It is not anything I'm going to consider. I'm going to consider only I'm going to save time, posing a constraint of time on the network, and then I'm going to go towards the output. That is my reinforcement learning method. Deep reinforcement learning, what does this mean? More the knowledge, more the parameters. In the example what I gave, the robot to climb the wall. To climb the wall, it will have so many parameters you have to readjust. Similarly, for me to reach one particular place, so many parameters like time, space, cost, length, I've considered so many parameters. More the knowledge, more is the depth. And there we call that as a deep reinforcement learning, which is very trending these days. Reinforcement learning, deep reinforcement learning, applications as with your playing games, Atari games and AlphaGo. These are some applications which are catching up these days. Now, what are the limitations of deep learning? So when I say any concept, we go on talking. I say neural network, I say artificial intelligence, I say machine learning, I say deep learning. Do you mean that deep learning is the ultimate solution? No. Even deep learning has got some disadvantages, or more than disadvantage, I can say limitations. Up to when deep learning can work. See, when the data is very large, okay, handling that in deep learning is difficult. And when the data is unstructured, what do you mean by unstructured data? What is the difference between structured data and unstructured data? Yes, all of you know the answer. I know that. In structured data, you've got a proper parameter, you've got a proper format for the data. When the data, when do you say it is unstructured? When you don't have a proper representation, like I have got data as an image, I have got a video, I have got a text, I have got everything mixed, and then I want to do data mining on that. Right? It is pretty difficult to have a representation like that. When the data is like that, it is very difficult to handle in your deep learning network. The next issue is the computational power. Training the neural network needs graphical processing unit, a GPU. GPU is expensive, okay, but that leads to a very good solution, which contributes to the computational power. That also is a limitation for your deep learning implementations. The other part is time. Deep learning will take hours. Sometimes they take even months to get trained. The time increased with the amount of data. The number of layers in the network will also increase. So now managing time in the deep neural network is also a challenge. Okay, so when your data is huge, when the computational power is more, and when the time is also factor, then deep learning will have to work out in a different way, and that is an area where deep learning is catching more trend these days, and improvement is a lot of improvement, and things are working with your deep learning representations. To conclude, we can say artificial intelligence, deep learning will have a major impact in our day-to-day living in future also. Specialized applications in various domains will have a very big thing in your deep learning representations, wherein we have specific applications in various domains we are trying to look into. And this is all I wanted to talk to all of you regarding your deep learning representations. Definitely, there are a lot of algorithms in deep learning. There are a lot of concepts in deep learning. And my session was limited to essentials of deep learning, areas of deep learning, applications of deep learning. Hope I've done some justice. Now I'm open for questions. Thank you, guys. Thank you all.
Yeah, thank you, ma'am. Thank you, Kavya, ma'am, for accepting the invitation and giving the insights of deep learning within the stipulated time given to you. Now the platform is open to get the responses to your queries if you have. Requesting participants to unmute yourself and get the responses.
Ma'am, good afternoon. What is computer vision, ma'am?
Computer vision.
Yeah.
Yes, ma'am. So let me explain. So now, as I told you, artificial intelligence could be of two different ways. One, we call it as a symbolic way of an understanding. The other one, we call it as a database type of understanding. Whenever you have got something called as database type of understanding, we have the concept of machine learning and all the things what we are discussing today about neural network, deep neural network, and all these things are a part of machine learning in neural networks under artificial intelligence, and all these are database type of representations. But when you get into the other major area of artificial intelligence, wherein we have got the concept of symbolic reasoning, there is where your computer vision comes into picture. Okay, in computer vision, like how our eyes will see the image. Once you see the image is cognized. Okay, the image, whatever image you have in your brain, it will try to make a mapping there, what we call it as cognitive sciences, and then that image is being processed using your image processing. That is also an area of your computer vision. Okay, computer vision is the start. When you recognize a scene, image processing is going to happen, right? Computer vision is more of symbolic reasoning, and it is an area of artificial intelligence. It is something like how your eyes work. Your eyes will capture the image, pass it on to your brain, and how that concept works. No, similar to that, we have to have computer vision. It's a symbolic vision, symbolic representation with cognitive sciences in artificial intelligence. Have I answered?
Well answered, ma'am. Thank you.
In simple, what are the human being having in terms of vision, perception, comprehension? The same thing which we are expecting from the computer through programming.
Yes, continue, sir.
Any more? Any more queries? If no queries, we will conclude the session. Oh, okay. I will post you the feedback attendance sheet for both the sessions 1 and 2. The participants need to be fill the form within the given time. Okay, if no more queries, thank you, ma'am, once again. Thank you for your nice presentation and sparing the time with us and disseminating the knowledge to all my participants. Thank you, ma'am. Yeah, thank you.
Yeah, thank you, Srinivasan sir, and thanks to all participants. Thanks for your patient listening, and thank you to all organizers of FDP and this institution for providing me an opportunity to share my knowledge on essentials of deep learning and its applications. Thank you all. You can always write to me. My mail ID I have shared with the organizers. I'm a researcher and working in this area of artificial intelligence and deep learning. So in case for doing projects or doing research, you want any ideas or you are stuck up with any progress, definitely I'm always there to help you technically. And thank you again for your valuable time. Thank you. Thank you all.
Thank
Ma'am,
you.
can you get your
Nice
PPTs?
one. Yeah,
Yeah,
ma'am.
hello, ma'am.
Rashita, ma'am.
Yes,
Yeah,
ma'am.
yeah, proceed.
Hello.
Yes,
Yeah,
ma'am. Please
proceed, ma'am.
tell.
Yeah, ma'am, I'm Professor Harshita from Pune. I just would like to have your, like, can we get the no, can we get your PPT, ma'am?
Definitely, ma'am. I'll share it right away.
Yeah.
Yeah, yeah.
Okay.
Ma'am, I
Thank
will
you,
get
ma'am.
all the slides from the resource people and the same will be circulated to all the registered participants.
Okay, okay. Thank you, sir. Yeah. Thanks a lot.
From them, we will do it as early as possible.
Okay. Thank you, sir. Thanks a lot, sir.
Yeah, now we will have the lunch break. Again, we will resume at 2 o'clock. Thank you all.
Welcome back. Now we'll have the talk on deep learning for face recognition, a practical session. And this session will be given by Dr. Mukesh Kumar sir from NIT Patna. We welcome you, sir, Mukesh sir, for this AICT sponsored online STTP program on machine learning and deep learning, sir, for day two session. We welcome you, sir. And
Thank
yes, sir. Before hand over the session to Mukesh Kumar sir, let me introduce him. Dr. Mukesh Kumar, he is working as an assistant professor at Department of Computer Science and Engineering, NIT Patna. He also worked at ABP Bangalore as a data scientist, and he awarded his doctoral degree in 2017. And he completed doctoral degree in CSC from NIT Roorkela in the area of big data and machine learning. Dr. Mukesh Kumar sir completed master's degree from NIT Roorkela, and he completed his internship at ABP Bangalore in the area of big data analytics and smart grid. He also had the publication around 10 journal publications, 3 SCA publications, and he also had one book chapter, and he had various publications in reputed conferences, 14 conference papers he had. And Dr. Mukesh Kumar sir is also as a reviewer of many journals like Elsevier, Springer, and In the Science. Yeah, sir. I Mukesh sir, I would like to invite you for this session.
you, ma'am. Thank you.
Yeah, you can continue with the session, sir.
I
Thank
am
you.
sharing my screen and continue the presentation.
Yeah, sir.
Is it visible?
Yes, sir. Yes, sir. Mukesh, sir, it is visible.
Okay, okay, okay.
Okay, so today we are going to study about the face detection in image processing. Then in the computer vision, we have a problem of recognizing the faces.
Keep it in full screen mode, sir.
We are trying our level best, but actually it is not giving me the option.
Zoom it, sir. Zoom the screen. Zoom the screen by scrolling.
Options.
Using much scrolling also we can zoom it, sir. Screen. Requesting participants to mute yourself. If you are in unmute mode, please mute yourself. Yeah, you can proceed, sir. Otherwise,
Is it visible to everyone?
yeah.
Is it readable condition or what?
Okay, okay. It is in readable condition only. No problem. But if it is incomplete, then yeah, okay, proceed, sir. No problem.
Actually, there is an issue while making it full screen. So I
Yeah.
don't know the current issue right now. So I'm
Okay.
taking this PPT from here only. Okay.
Yeah, proceed, sir.
If someone has issue, please let me know about that
Yeah,
at any moment of time. Okay.
yeah, sure, sure. Right.
So we are just starting about the discussion on face detection in computer vision problem. So what is actually the face detection is we are taking this problem as a abstract level, the object detection. In an image, when we talk about the object, it can be anything, whether it could be a person, face, anything, personal thing, or physical thing, anything like object we are looking for. So we need to identify where the object exists in an image. So object detection is a combination of computer vision problem and image processing. So it includes the classifying an object in the image and check the position of the image, where it is localized in the image. So this is done by the segmentation. So we are going to discuss about the segmentation in next slides, like panoptic segmentation, instance, and semantic segmentation. So how this face detection looks like actually. So in current research, the face detection looks like the this way. You can see this image. We can localize the face position. We will classify the object that this is the face over here. Now we will localize their features, facial features like eyes, nose, lips, ears. We will localize them as well. So it's not about just only to classify the face and localize the face. We need to identify which face is this. So we are going to discuss this research over here in further slides. How this is going to be achieved, we use segmentation in recent researches. So I have used two segmentation over here, semantic segmentation and instance segmentation. To distinguish between these two, we can see this thing. In an image, there are 5 persons standing over there. So as a similarity person, that all these persons belong to one class, that is person. So we segment out all the person with the same color. So this is known as semantic segmentation. The similarity between the objects will be classified as one object. In instance segmentation, every single object will be segment out. Every single object will be segment out. So this is the difference between these two segmentations. And we talk about panoptic segmentation. We will use the merge of semantic segmentation and instance segmentation over there. These are the latest segmentation technique we use in any object detection technique. So how this object detection actually works? So we will take this combination over here. Wait, I guess full screen background is here. Now is it full screen visible to everyone?
Yes, sir. Proceed.
Okay. Okay, now is more clear to everyone. So what we do, we will in the recent years, what we do from the image, we will classify the object, whether the presence of an object over there or not. In the first image of classification of cat, we will just classify whether the cat is present in the image or not. So we have some simple data set where the number of objects will be defined, and in each image we have the class labels whether the this image contains which object. So we'll do classification using convolution neural network, and later that problem will be more challenging when we need to localize the object. Now we have classified the object that cat is existing in this image, but where the position of the cat? Okay, so that is known as localization. So in the second image, the red rectangle can be seen as the position of the cat in the image. So now the classification and localization of the object is known as object detection. So it can be for single object and multi-object. So in the third image, we can see this thing. The red objects are the cat, and the blue object is for dog, and the yellow is the green box is for the duck. So we have 3 objects segmented out, and we have, and not segmented actually, we have detected 3 objects over there with their different boxes, blue, green, and red. In the instance segmentation, we have classified these objects and their positions with pixel wise. You can see there is a difference between this object detection. You have some extra background over here, but in instance segmentation, we have only object, no background is included in this segmentation result. So we'll see in the practical session how these things will be achieved and how these actually the data input and everything we will discuss over there. So for the first we will see how this classification works. So the basic standard example we can use for the classification purpose is this MNIST data set with a LANet architecture. So we have some numeric images where from 0 to 9, and we will use some convolution operations, and at the end of these convolution layers we have flattened the layer and use the fully connected network to classify the object, to classify the number present in this MNIST data set. So this convolution operation, just to for the brush up purpose, I'm using, wait, convolution operation. So how this convolution operation works? So we have some fixed size kernels. Let's say we have used over here 2x2 on this 4x4 image. So we have mapped this filter on the image. So we have multiplied, we have to calculate the dot product in this convolution operation. So A with W, B with X plus C with Y and so on. So we'll together get the dot product in one node, which is known as the feature. So we'll easily identify over here, see this thing. The calculation you can see, this blue, dark blue over here will be mapped with this kernel filter, and we will evaluate this value in the feature first row, first column value 51. We'll compute this with multiplication, the dot product between two matrices. So we will find out the features metric. These features are actually the shallow features, and when we do this convolution operation going on, we will get the deep features over there. So we'll see these things. This is another operation we use in convolution operation, that is pooling, to reduce the number of features, because when we use convolution we can use that, see this thing, the number of layers over here around 512, the number of features we can see 6 over here, 14 over here, and so on. So we have so many number of features, we have to reduce these features over here. So we use pooling to do this operation. So max pool and average pool we generally use. So the max pool, the result of max pool, we have used these 2x2 filter with a stride of 2. The stride means the shifting of this filter. So from this blue matrix we get the maximum value of pixel as 9. So that is how we reduce these features. And from the green matrix we got this value 7, and from the yellow matrix we got the maximum value 8, and from the red matrix we got the maximum value 6. Similarly, in average pool we'll calculate the mean of this blue matrix, and the mean value will be over here. That's how we reduce the features in convolution operation. Now another thing in object detection what we use over here is classification purpose. We have image, we put the class label over there, the loss will be calculated using cross entropy, and the evaluation metrics we use accuracy. The simple technique of neural network, the evaluation matrix is accuracy. For the localization purpose, we again have the image input. Output box is the image, let's say the coordinates of these box. As per the data set, we can have X coordinate, Y coordinate, width and height. The width and height of this box, and XY coordinate of the center. The loss will be calculated by the Euclidean distance. The Euclidean distance is nothing but just the distance between 2 points. And when we talk about in the higher dimension, the distance between the planes and hyperplanes is the Euclidean distance. And the evaluation metrics for the localization purpose, we use intersection over union. We'll discuss this intersection over union because this is very new thing right now. Mainly the people know about accuracy, but intersection over union in localization technique we use over here. In the object detection, we combine this two things, classification and localization. So we have image. In the output, we have the class label. We need to identify which object belongs to which class, and the box dimension, X, Y, with height, or we can use all those 4 coordinates. And loss will be the sum of both losses, that is known as cross entropy plus Euclidean distance. This is known as the combination of these 2 losses. It will be compute this thing in object detection technique. So here it is the cross entropy method. I also use this term as log loss. So this will measure the performance of a classification model whose output of a probability varies between 0 to 1. So this loss actually getting large when we have the class level very low. The probability value is very low. The another loss function we use is Euclidean distance. As I said, the distance between two pixels, and when we talk about the higher dimensions, it will be the distance between hyperplanes. That is how the Euclidean distance will be computed. Now, when we talk about the face recognition, so we will put the face image in the input size. The features will be computed through the number of filters we can use. For each feature, we will get each kernel, we will get the one feature map. So in the feature 1, you can see this 3, 3, 6, 24 features over here. In the next feature 2, again 24 features are there. But the feature 1 and feature 2, the difference between them is the feature 1 is very shallow. The features over here is rarely can distinguish about the face, but when we go deep into the network, the last layer features are actually used for the classification and localization purpose. So as I said over here, the shallow the features in the beginning and the deep features at the end of the network. We have used convolution operation, max pool, ReLU layer, as well as the dropout layer, just to reduce the overfitting over here. So we will use these four mainly. Now the object detection with simple methods, we can use this thing. Well, I hope everyone has heard about the VG16 network. So I have used, for the example purpose, this convolution and pooling, this trapezium box. You can assume this trapezium as a VGG16 network. So input image will give you the final convolution feature map. This feature map has some volume. So this is, let's say we have some 9 cross 9 cross 512. The 512 is the volume of this feature matrix of 9 cross 9 each features. So we'll put these volume in fully connected layers for the classification of the object, whether the object is present in the image or not. And another fully connected layer we'll use for the regression purpose to identify the box of the object. If the class is present, if the object is present over here, we will get the box around it. So the dimensions will be x, y, w, h. That is, the xy is the center point, width and height. The box values we will get from the regression part, box coordinates. So now intersection over union, the evaluation matrix we use. So what we have to provide for the object detection, the annotation part. So let's say we have this image, this object detection image. We have some cat over here, another cat behind it, one dog and one duck. So we need to create a annotation, a box kind diagram around the object. So we have provided some annotation that one cat is present over here, the another cat is present over here, one dog is present and one duck is present. So we'll provide the annotations, we will provide the dimensions over there where the coordinates will be mentioned, the image number will be mentioned, the data location will be mentioned in one annotation file. The standard data format is, you can use Pascal, VOC and Cocoa data format. We'll tell you how these annotations has been done. So for the intersection over union evaluation purpose, what we do, we have some annotation for the ground truth purpose. Let's say this blue rectangle defines the ground truth, whereas the pink rectangle defines the result rectangle where the object presented. So we have green rectangle over here for the ground truth and the pink rectangle for the resulted. So surface of intersection, that's purple portion, the intersection part, and divided by the union of it, the blue, you can use shape. These value will be used for the evaluation purpose. This ratio will tell how much coverage of result is, how much coverage for the object is going to result it. So the algorithm is very simple over here. What will get the output, the probability of the class and the coordinates around the class, these four coordinates, and the class label, the C1, C2, and the number of class labels. So for each class label, we'll get this probability value. So we'll have some threshold over there. Let's say we have threshold, let's say 0.6. So if the probability of the objects will be greater than probabilities of the threshold 0.6, then we'll assume in this image we have these many objects. So let's say we have one object in the image, we will have one probability over there. If it is greater than 0.6, so we will assume that object is presented over there, and we will compute the box dimensions, that is bx, by, bw, and bh. For the IOU purpose, intersection over union, we will assume that it should be greater than 0.5. So we can modify this threshold values up to 0.8, 0.9 as per our requirement, how confined our object present over there. So basically we use in research purpose, if the number of objects is less in the image, we'll set this threshold less. If the number of objects in the image is higher, we'll set this threshold is maximum up to 0.8 or 0.9. So anchor box concept is there when we use to draw the boxes over there. So anchor box, let's say we'll define in YOLO model. So I'll continue this, discard the remaining boxes concept over there. So we have one Siamese network in face recognition. So what we do in Siamese network, we have two similar models, the same model. The input image will be fed to both these networks, and the output will be computed with the Siamese distance, similarity distance. So the purpose will be identified later. Just for the evaluation purpose, just assume this thing. We have image I1, and I1 image will be fed to these two model, M1 and M2. The similarity between these two images will be computed and the score will be generated. The result is actually put in the database. The reason is, since we cannot have the number of images for the same purpose in the database, to recognize an object, we can have one image of the person, and for every time when we get the image of that same object person, we'll pass that image from this network, and the similarity between the existing image we have in our database and it is the computed value, and the similarity distance will be computed between the dataset image and the computed from the network. Another network what we have in face detection is YOLO based face detection. As I said, YOLO means you only look once. So what YOLO do, we have the input image and it will result it into the 9x9 volume of the feature matrix. So each feature will be divided into the 9x9 grid, and each grid is again passed to the another auxiliary network for the detection of face. So if any grid contains the center point of the face, so we will use that grid for the object detection or the face detection purpose. So each grid has 5 associated values. Let's say we have some 5 values: center point, the presence of object, height, width, etc. So this is what the architecture we use over here, that in the first layer we have 8 filters, and the input image size is 288 cross 288. The max pool layer for the 2x2 we have used. In the similar fashion, we have used 16 filter in the second layer, 32 in the third, 64, 128, and 192, and so on. At the end of these convolution operations, we'll get the 9x9 feature map. The volume of this feature map is 5. At the end of the line, you can see 5 filter convolution layer on 9x9 feature map. The volume of this end result is 5. So we have 5 features of 9x9. So this 5 volume will be again put in the auxiliary network. So what we do, this auxiliary network will identify whether the object or the face present in each grid. Since we have divided the image in 9 grids, 3 cross 3, so we will identify the center point of each face. So for the object detection purpose, what we get, the using intersection over union part, we get the object and some confidence score around this object boundary. So you can see this, the confidence score 1, 0 point, it is always less than 1. It is a probability over there, the confidence score. And this is what the evaluation purpose we use: average precision, average precision AP. So we have some scales: small, medium, large, and recall, and the same recall for the small, medium, large. So these are the terms we are going to use for the evaluation purpose. The average precision is going to be calculated by this formula, the summation of all the recall and precision multiplied divided by the recall of the present object. Similarly, the mean average precision for the entire model will be computed, which will be result the efficiency of each model. For the face detection purpose, we have number of models which has computed this thing. These are the different models as I am talking about. These are the mean average precision we have computed. Now we will look about this application. We use over face unlock, person identification, and video surveillance of face detection. Now we will look how we are going to implement these face detection. In the theory part, is there any doubt, or we can move to the practical session?
Yeah, participants are requested to clear your doubts if you have so far. Yeah, proceed, sir. Continue. They might be asking at the end of the session.
Okay, sir.
Proceed. Thank you.
This is one annotation tool over here. So what we do, we will annotate our data from using label me, label img, and one online tool from the Stanford University we have. So we can design these things. Let me do this thing for you. Let's say one image is here. So we can annotate each and every line, or we can use object over here. Anything can be present. So we will create some polygons around it. So you can see this thing. A rectangle, anything shape, we can give it to it. So we need to define the annotation of each object. Let's say we have defined this object as object 1. So you can see the label list contains the object 1, and we will have some dimensions of this object 1 in the annotation part. The another annotation, we can conduct these annotation. For each image, if we don't have public dataset, we need to annotate our images just to make the private dataset valid for this models. We need to provide the annotations as well. So these annotations will be fed as the input in the model. So in the JSON format, this is the Pascal VOC format .json, and for the YOLO purpose, we have Coco format .xml files. So we can have these .json files. Let's say we have stored over here. So how this files will be seen? Let's see this thing. Now, see this. Each annotation will define the labels of the object and the coordinates of each and every object, the annotation. So these are the x and y coordinates. And here you can see the path, image path. Here you can see each and every file contains the image name and the path of image. So we can have the entire details. It can be used as a metadata about the image. So we have to provide this metadata in the model to define every object location, the image name. We have to save these files with the same name of same image name. Let's say we have used 004 as the .jpg. So we have saved this 0004.json in the similar fashion so that to identify easily which annotation belongs to which image. So this is one annotation tool we have. Another annotation tool we have in Stanford University. You can use that tool online easily. Another thing over here, we can directly take these things. If we need to avoid the polygons, we have some predefined shapes to identify the object. Let's say a circle. So it will create a circle around the object, and the same object one we can edit these things. If we want to rename some another object, let's say object 2. So object 2 will be added over there. The label list will contain the number of objects present in this image. So we have some two objects present in this image, object 1 and object 2. The coordinates of each object will be defined in annotation file. So we can again save this file. We can visualize the annotations. As you can see, the image 2 contains the radius and the circumference values, the coordinates of these two circles. We have circle values. So we have different annotations around it. For the practical session, I'm going to take you in the Google Colab, which is easily available for the GPU purpose. Let's take a 2 minutes break to digest this theoretical part, and we will continue with the practical session soon with this 2 minute break.
Yeah. Okay. Okay, sir.
Okay, now we will start the practical session. So these annotations actually are the Y labels. In the neural network, what we do in the classification, we have X, the independent variables, and the Y, the dependent variable. These annotations and the class labels are actually the dependent variables. For the classification and localization purpose, we need to provide the dependent values. So for the training purpose, so we are providing these annotations, and that is why we are doing this annotation for each and every image. Once the model is designed, we need not to do annotation for the testing purpose. We can use these model for our practical domain. So as of now, I have these darknet and each and every data structure. We have the folder structure, but we will continue with from the scratch how we are going to use these things. So I'm getting one directory of darknet of YOLO. The YOLO is actually started from the darknet, the basic model. So we are getting one directory of the darknet. So once you will clone this directory, this already exists. Okay. So we can remove such thing. So we have some darknet folder over here. So after cloning the darknet directory, we need to define the required libraries, let's say OpenCV, GPU configuration, and the CUDA library. So we'll make a file over there just to identify the configuration. Each and every time we need not to define the configuration. So once this make file is made, we can install all these dependency from the makefile. So we'll run this makefile in the furthest code. So this is what the makefile looks like. Once we will create this makefile, the makefile will be present in this darknet folder. So you can see this dependency over here. The GPU will be one, the CUDA requirement, the OpenCV, all these dependencies will be mentioned over here. The configuration of GPU, the GPU equal to 1 defines the requirement of GPU. If it is 0, it will use the CPU, and if it is 1, the GPU will be required to run this program. Other dependencies like the architecture or the processor required, we can have from here. The path of the data set, everything will be defined in this makefile, so that no further error or dependency will be required. Just to get the YOLO model, what we are doing, we are downloading the YOLO version 3 weights in our folder structure. We have our model over here. To initialize the weights from the scratch, or we can use the existing YOLO v3 weights based on some predefined data set, we can download directly, and further training will be continued from these weights. So it can avoid our training, it can reduce the training time we need. Since my internet is very slow, we can interrupt this thing. Once this will be downloaded, this can be reflected in our folder structure. since we cannot accommodate this 46 minute. Now, just for the purpose of makefile run, we have used this command, and all the dependencies will be required, will be downloaded and installed. Now it will create the configuration we require to run this program. Till now, is there any doubts related to the code, why we are creating this configuration or anything? Since this makefile execution requires some time. All the hardware related dependencies like GPU configuration, the CUDA configuration, the versions of the libraries, everything will be downloaded. Now it is completed. Just for the sake of folder structure, we are looking where we are actually presented. So we are in the folder of darknet. So now we can continue our further execution. Since, as I said, we have downloaded the weights earlier. So from the data, we are actually putting these person.jpg image. We are detecting this, whether this image is present or not. So that is why we are running. Again, time consuming the code. So in the further code, we have two functions to show display the image. Where we'll call these functions when we need to present our results. And one function is for the uploading the data and downloading the data. So if we have predefined data, the public data set, we can download directly. Or if you have custom data, as we have done annotation and everything, so we can transform that custom data into the public dataset format like Pascal VOC or Coco dataset format. These things will be easily available online. So you can transform your own custom data into the public dataset format. You need to interrupt this execution to execute the further functions. As these GPU related codes are very much time consuming. That is why the reason we use online easily available GPUs, or we need to have some good value CPUs. Now it is running very fine. It is giving you the values of features, how those architecture is defined, the layers, the number of features, the number of filters, the convolution functions, everything we are defining over here. Yeah. See, as we have downloaded all the weights of the YOLO model and we have passed our data to this model, so the test image, we have one image, and the annotations of this result model, we can see this dog is present over here with the confidence score of 0.99. That is very much high. One person is identified over here with the confidence score of 1, one horse with the confidence score of 1. So that is how we are actually getting our results. So you can train your model with the custom data set, and this model training will require huge time as depend upon your data set size. So you will get these values. So other than this YOLO model, you can use faster RCNN, fast RCNN, mask RCNN. These are the different models you can use. So if we have some face recognition image, it will identify the face, number of faces present in this image, and the facial features. If we need to if we have the annotations around it, the position of eyes, the number of eyes. If we have one eye image, let's say the person is tilted or the image is taken from the one different angle. So those annotations we need to provide every time for each image. This is another example of annotations. See, for this image, we have three objects: the dog, the cycle, and the truck. The confidence score corresponding to each box is mentioned over there. Similarly, if we have different types of objects, we'll classify those objects and their localization. And the facial features, if we need to, we can identify those facial features. And according to that, we can identify the person as per the facial features. Is there any doubt till now in practical session? Till now, any doubts in practical session or theory session? Revati ma'am,
Yes, sir. Tell me, sir.
is there any doubts of any participant,
Participants, please ask any doubt.
or we can stop from here?
Question is open in question doubts. Please ask questions. Participant.
Yes, we can share the notebook. Just provide me the email ID, or we can share with the organizer. They will distribute the notebook. We'll provide you the resources, not the PPT. For the studying purpose or for the learning purpose, we will provide you with the resources. Yes, we can provide those related materials, everything. We will share with the organizer. So, ma'am, can we end up our session over here?
Yeah, participants, can you ask any doubts? Hello, participants, can you ask any doubt? Yeah, can you wind up, sir?
Okay.
Okay, thank you, sir.
Thank you, everyone, to join this session.
Yeah, thank you, sir.
Hello, Mukesh sir. Hello, Mukesh sir.
Yes.
Hello.
Yes.
Yeah, sir. If possible, could you provide the resources like online tools or database regarding face recognition to the participants?
Yes, we will share soon.
Yeah. Share some resources which helpful to the participants on this particular topic.
Okay.
Online tools, data sets regarding or any stuff to be followed that may help to the audience.
By the end of the day, we will provide all the resources in
Yeah.
one mail. So we will get these things. Every
Yeah.
participant will get it.
Okay. Yeah. Actual session is scheduled till 3:30. Participants, if you have any
Actually,
doubts,
we are
right.
on a
Yeah.
very fast pace. So we have concluded very soon.
Okay, no problem, no problem.
Hello,
We're
sir.
trying to give the,
I have got one question, sir.
yeah,
Yes,
proceed.
please.
Sir, can we run this OpenCV in Windows 10 or
Yes.
Linux is important?
Yes. OpenCV doesn't have some dependency on CPU or anything.
Okay. And what about YOLO, sir?
YOLO, for the YOLO purpose, if you are running on the CPU, you can. But as soon as the data size is increasing, the speed of the model and the computation will be large.
Okay. That means Windows is not a problem, right?
No, not at all.
Okay. Thank you, sir.
Okay, so what Sars is telling is that operating system constraint is not there. It is about we need to see the computational and the storage capacity. Operating system constraint is not there, right?
Yeah.
Yes.
Okay. Thank you, sir. Thank you, sir.
Any more, sir? Any more queries from the participants? Please clarify your queries from the speaker.
Sir, which book is better, sir, for this face recognition? Sir?
You can use online resources. So many online resources directly will get you to know.
So any difference between image processing and this one, face recognition and all that? It's coming in the same domain, sir.
The image processing is the actually broader
Yeah,
concept. For
yeah,
the face recognition is the main deeply you can use.
yeah. One of
O-
the application of the image
Computer
processing.
vision problem, you can say.
Yeah,
Okay.
yeah. Face
Okay,
recognition
sir.
is specifically can be done with the deep neural networks, sir. If you are asking for the more accuracy
Yes, sir.
with large data set, it comes under deep learning, sir. Deep neural networks is required to handle the face recognition. This is one of the application of image processing. Image
Okay, sir.
processing is very broader. There are many unlimited applications are there where input image is taken as input and output is depends on the user.
Okay, thank you, sir.
Yeah, due to computational advancement and the programs advancement, we are able to do the things with convenient manner. Before that, we don't have these type of resources. If no more queries, we will conclude the session and we will close it. We will meet at 10 a.m. tomorrow. Thank you one and all for your active participation.
Thank you, sir. Thank you,
Yeah,
everyone, for joining the session.
yeah, thank you very much. Thank you for accepting our invitation and doing the insights of the topic given to you, sir, titled Deep Learning for Face Recognition. Thank you for your informative presentation.
Thank you, sir.
Thank you. If possible, share the resources related to this particular context so that we will forward it to the participants.
Sure, sir.
Yeah. Thank you very much.
With this list of achievements, I would like to welcome Dr. Kavya Madam to this STTP. We welcome you, ma'am. I request you to take over the session and continue, ma'am.
Yes, ma'am. Am I audible, ma'am?
Yes, ma'am.
Allow me to share the screen.
You can share, ma'am.
Okay, is it visible, ma'am?
Yes. Yes, madam.
Fine. So thank you for that wonderful introduction. And good morning, participants. Today, I'll be delivering a session on essentials of deep learning and its applications. Ma'am, my voice and the screen, is it fine?
Yes, madam. Fine, madam. You can continue.
So myself, I'll be taking you across the different issues in deep learning and also a little bit of applications of deep learning. So let us start the session. Uh, Participants, can you look at the screen? Can you recognize who is this? Unmute yourself. You can talk to me. Yes, this is, if you just look at this, you can make out it is Aishwarya Rai. Most of you probably, yes, you got the point, right? So that even without showing you the complete image, your mind was able to make out. You could recognize the image, and a deep learning is like a neural network only initiated, wherein you're trying to, and also, for instance, it is limited to essentials of deep learning, areas of deep learning, applications of deep learning. Hope I've done some justice. Now I'm open for questions. Thank you, guys. Thank you all.
Yeah, thank you, ma'am. Thank you, Kavya, ma'am, for accepting the invitation and giving the insights of deep learning within the stipulated time given to you. Now the platform is open to get the responses to your queries if you have. Requesting participants to unmute yourself and get the responses.
Ma'am, good afternoon. What is computer vision, ma'am?
Computer vision.
Yeah.
Yes, ma'am. So let me explain.
Dr. Mukesh Kumar. He is working as an assistant professor at Department of Computer Science and
greater than 0.5. Once we will create this one image and the
Ask any doubt.
we can till now any doubts in practical session or theory session? Revati ma'am,
Yes, sir. Tell me, sir.
is there any doubts of any participant,
Participants, please ask any doubt.
or we can stop from here?
Session is open in question doubts. Please ask questions. Participant.
the email ID, or we can share with the organizer. They will distribute the notebook. So, ma'am, can we end up our session over here?
Yeah, participants, can you ask any doubts? Hello, participants, can you ask any doubt?
We have finished earlier.
Yeah, can you wind up, sir?
Okay.
Okay, thank you, sir.
Thank you, everyone, to join this session.
Yeah, thank you, sir.
Like online tools or data resources like online tools or database regarding face recognition to the participants?
Yes, we will share soon.
Yeah. Share some resources which helpful to the participants on this particular topic.
Okay.
Online tools, data sets regarding or any stuff to be followed that may helps to the audience.
By
Hello, sir. I have got one question, sir.
Yeah.
Yes, please.
Sir, can we run this OpenCV in Windows 10 or
Yes.
Linux is important?
Yes. OpenCV doesn't have some dependency on CPU or anything.